Welcome back. Let's review for your Calculus 2 final exam. Alright, so in this video, we are going to work through some review problems to help you prepare to take a final exam in Calculus 2. Specifically in this video, I have 15 review problems that we're going to work through, and there are an additional 15 problems available exclusively on my membership site. I'll talk more about that at the end of this video, but in total, between this video and those extra examples there, that would be a total of 30 problems, which is probably more than you would actually see on a Calculus 2 final exam, but this is not meant to necessarily mimic your final exam, but rather help you prepare for it. Okay, and before we get started working through these different review problems, there's a couple things I want to make sure to mention. The first thing is that if you want to get the most out of this video, I highly recommend that you try each and every one of these problems for yourself first before you watch me work through them. Really try to challenge yourself, or maybe you want to treat the problems in this video as if they were your Calculus 2 final exam that you were going to be graded on. In fact, I have a free worksheet set that you can download that goes along with this video. It has all the review problems that we are going to take a look at, so you can download the PDF and print it out and use it as a practice exam if you'd like. And so if that's something that you would like to have as you watch through this video, feel free to download that free PDF. The link for it will be in the description of this video. Okay, so that was the first thing I wanted to mention, but the second and final thing is that this is a review focused on the major concepts covered in a typical Calculus 2 course, and that's it. So that means we're going to look at problems related to applications of integration, advanced integration techniques, sequences and series, calculus of parametric curves, and calculus of polar curves. Okay, so basically everything I covered in my Calculus 2 video series. And so if you haven't watched the majority of those videos, or if you're not familiar with any of these concepts, be sure to do that first. Be sure to get familiar with these concepts. Otherwise, these problems are going to be pretty difficult and you won't quite know what you're doing. In this video, I'm going to assume that you know the concepts that we are working with. I'm not going to explain everything from scratch, but obviously I will give you some reminders here and there about different formulas or the way that certain things work. But ultimately, to an extent, I'm going to assume that you know what we're talking about. And with that being said, I think that's everything I wanted to cover before we get started here. If you're going to take my advice and try these problems out for yourself, then get ready to pause the video because I'm going to get started now. Let's move into our first final exam review problem. Okay, so for our first review problem, we want to determine whether the following sequences converge, and if so, find the limit. And we're given two different sequences to work with. We have a part A and a part B. Let's just focus on part A to start. We are given a sequence cosine of n divided by n, where n starts at 1 and increases towards infinity. Alright, now remember, a sequence converges if the limit as n approaches infinity of the nth term is equal to some finite value, meaning it's not infinity or negative infinity. And so whatever the value of that finite limit is, will be the value that the sequence converges to. Okay, so what we want to do here is take the limit as n approaches infinity of cosine of n divided by n. And so looking at this limit, what happens to this expression as n approaches infinity? Well, in the denominator, we just have n, so if n is approaching infinity, then that denominator will be getting bigger and bigger. It will be approaching infinity as well. So far this is equal to something divided by infinity. But what is in the numerator? Well, it's cosine of n where that n is approaching infinity. In other words, the input for the cosine function is getting bigger and bigger. And something that's interesting about the cosine function is that its output does not get bigger as the input gets bigger. In fact, the output for cosine is always between two particular values, right? If you were to look at the graph of cosine, it would look something like this, right? It has these different waves that continue on forever in both directions. But for that curve, it will always lie between y equals positive 1 and y equals negative 1. Right? The output for the cosine function will never be bigger than 1 or smaller than negative 1. So it doesn't matter that the input values, in this case n, are getting bigger towards infinity. As you choose bigger and bigger input values, the cosine function will just continue to oscillate between 1 and negative 1. So there is no clear value that results from cosine of n as n approaches infinity. We know that it's always going to be between 1 and negative 1, but we can't choose a specific value that that limit would be equal to. Okay, so this numerator causes a problem. We're not quite sure what that would be equal to. We know that it's going to be a small constant value that is being divided by infinity. So from intuition, you can sort of see that this would approach 0 because when you have a fixed number divided by an increasing denominator, or in other words, infinity, for a limit that will approach 0, but we can't go straight to that conclusion here. We can't just say that this limit is equal to 0 and call it a day. We have to show somehow that that would actually be the case. And so what do we do here? How do we handle this limit? Well, what we have to do is make use of the squeeze theorem. And here's what I mean by that. As I mentioned earlier, we know that cosine of n will be between +1 and -1, right? -1 will be less than or equal to cosine of n, which is less than or equal to 1. So what we can do is make use of this fact and compare this expression, where cosine is being divided by n, to two other expressions, one of them being -1 divided by n, and the other being +1 divided by n, right? We can make the following statement. We know that cosine of n divided by n would have to be less than or equal to 1 divided by n, and greater than or equal to -1 divided by n, right? Because cosine of n, as we just wrote down, is between -1 and +1. And so if you divide each part of that inequality by n, then the inequality will still be true. Of course, assuming that n is not 0, which in this case it's not, n starts at +1 and increases towards infinity. So this is a true statement. We are allowed to say this, but then what we can do is take the limit of each part. And this is where the squeeze theorem comes into play. If the limit as n approaches infinity of these two expressions are equal to the same value, then the limit as n approaches infinity of cosine of n divided by n will also have to be equal to that same value. Okay, so we're going to look at the limit as n approaches infinity of -1 divided by n, and that will be less than or equal to the limit as n approaches infinity of cosine of n divided by n, and that will be less than or equal to the limit as n approaches infinity of 1 divided by n. Now hopefully you recognize this limit here, the limit as n approaches infinity of 1 divided by n. We know that that equals 0. You have a fixed value divided by an infinite denominator, right? N is approaching infinity. So you can think of this as being 1 divided by infinity, which within the context of a limit, we know approaches 0. And the same thing for this limit. It doesn't matter that you have -1 divided by n, where n is approaching infinity. You still have a fixed value divided by an infinite value, or a denominator that is approaching infinity. So for a limit, that value will approach 0. As that denominator gets bigger and bigger, -1 divided by that value will get closer and closer to 0. So what we get here is 0 less than or equal to the limit as n approaches infinity of cosine of n divided by n is less than or equal to 0. And this is pretty neat because now what we have just shown is that the limit as n approaches infinity of cosine of n divided by n has to be between 0 and 0, which means the only possible value that it could be is 0, right? That is the idea of the squeeze theorem. We squeezed this function between two other functions that have the same limit, so that means that this function must also have the same limit. And so that leads to our final answer here. We can now say that the limit as n approaches infinity of cosine of n divided by n equals 0, and that was by using the squeeze theorem, which means that for our sequence, since that limit is a finite value, the sequence converges, and it specifically converges to a value of 0. All right, so as these values of n get bigger towards infinity, the value of the terms for this sequence get closer and closer to 0. Okay, so our final answer here is that the sequence converges to 0. Okay, so that is the final answer for part A. But now what about part B? We have a different sequence here. This time we're just given the terms of the sequence. We don't have it written out using this notation. So our approach here will be a little bit different. The first thing we want to do, if possible, is figure out what the nth term of this sequence would be and write it out with this notation, and then take the limit of that term as n approaches infinity. And in order to do that, we have to identify a pattern in these terms. Okay, and so looking at the terms, the numerator is always the same. It's always 1, so nothing changes there. We know that in our nth term, that 1 will be in the numerator. But what about the denominator? What is going on in the bottom of these fractions? Well, for the first one, we just have 4, then we have 16, then 64, then 256. Notice that they are progressively getting bigger and bigger, almost to an exponential extent. And in fact, that is exactly what's happening here, because we know that 16 is 4 squared, 64 is 4 cubed, and 256 is 4 to the power of 4, right? Another way that you could write these terms is 1 divided by 4 to the first power, and then 1 divided by 4 squared, and then 1 divided by 4 cubed, and then 1 divided by 4 to the power 4, and so on. The next term would be 1 divided by 4 to the power 5, then 1 divided by 4 to the power of 6, and it would continue on from there. Okay, so we can think of this first term as being the n equals 1 term, then this term is the n equals 2 term, and then the n equals 3 term, the n equals 4 term, and so on. So the nth term for this sequence, and I am going to put it in the notation, it would look like this. We would have 1 divided by 4 to the power of n, starting with n equals 1 towards infinity. Okay, because remember, for a sequence, we are assuming that those values of n are integers, and so we go from n equals 1 to 2 to 3 to 4, and so on. This would be the notation that represents this sequence. But then the question is, does this sequence converge? Well, we can determine that by taking the limit of that nth term as n approaches infinity. All right, so we'll take the limit as n approaches infinity of 1 divided by 4 to the power of n. And so what happens to this expression as n approaches infinity? Well, you'll have 4 raised to a higher and higher power. And as you raise 4 to a higher power, it will become a bigger and bigger value. All right, that denominator will continue to get bigger and bigger as n approaches infinity. And so you could say that this limit is equal to 1 divided by infinity, which within the context of a limit, we know that that approaches 0. And so the limit as n approaches infinity for the nth term of this sequence exists. It's equal to 0, which means that this sequence does converge. Specifically, it will converge to 0. So we actually get the same answer as we did for part A. What we have found here is that the sequence converges to 0. Okay, that is the final answer for part B. And with that, we are now done with this first review problem. We were able to determine that both of these sequences converged, and we found the limit that gives the value that they would converge to. Let's move on to our next review problem. For the second review problem, we're going to let V be the volume of the solid that results when the region enclosed by y equals 1 divided by x, y equals 0, x equals 2, and x equals b, where b is between 0 and 2, but not including those values, is revolved around the x-axis. Find the value of b for which v is equal to 3. Okay, so this problem does look pretty complicated at first glance, but it's actually not too bad. Let me show you. First of all, do notice that we are given a picture that shows us the region that is going to be revolved around the x-axis. In fact, I'm going to label that here. We're going to be revolving a region around the x-axis to form a solid of revolution. And that region is enclosed by 4 different boundaries. We have the curve y equals 1 divided by x, and we're only looking at part of it here. There is more to that function in the negative direction, but we're just looking at the part of it in the first quadrant here. And so we have that curve along with the line y equals 0, which is the x-axis. So the region will not go below that x-axis. And then we also have the line x equals 2, and then this other line x equals b, where we don't quite know what the value of b is. In fact, that's what we want to solve for in this problem. Okay, so this is just a representation of where that boundary line may be. We're not exactly sure, that's what we have to figure out, but we do know that b is between 0 and 2. So we know that that other boundary line will be somewhere between the y-axis and this boundary of x equals 2. And it can't be equal to the y-axis or x equals 2 because b is just greater than 0 and just less than 2. Okay, so that line will be somewhere between those two values of x. And the specific value of b that we're trying to find here is when the volume of that solid of revolution is equal to 3. Okay, so what we probably want to do here is set up the formula that would calculate the volume of that solid of revolution, set it equal to 3, and then solve for b. Right? Usually in volume problems, we are calculating the volume, but since we are given the volume, we're going to be able to set that equal to our formula and solve for something else. And remember that we have a couple different ways to calculate the volume of a solid of revolution. We have the disk method, washer method, and the shell method, although really the disk and washer methods are essentially the same. But we do have a choice between those methods and the shell method, and so which of those do we want to use here? Well, it looks like we want to work in terms of x, right? We're going to set up an integral that will calculate the volume of the solid of revolution, and it will make the most sense to work in terms of x, because the two bounds of integration could be x equals b and x equals 2. Right, the region that we're working with lies between those two values of x. And then we only have one curve that is also already in terms of x, for which the region is below. Technically, there is a second curve or a second boundary, that being y equals 0. But as you're going to see in just a second, that's not really going to matter too much. But regardless, my point here is that we want to work in terms of x, and the region is being revolved around the x-axis. So when you want to work in terms of x, and you're revolving around the x-axis, you want to use the disk or washer method. The shell method is more helpful when you are working in terms of x, and the region is being revolved around the y-axis, when it's the opposite of our scenario here. Okay, so let's set up the formula for calculating volume using the washer method, or as you'll see, it's really going to be the disk method, because one of the boundaries of our region is y equals 0. But normally, we have that the volume is equal to pi times the integral from a lower bound a to an upper bound b, where those are both values of x, of the outer radius squared, represented by capital R of x. So you take that outer radius and square it, and then subtract the inner radius squared, which we represent with small r of x, and then don't forget about dx. Okay, so in our scenario here, the outer radius, capital R of x, is what I've been referring to as this upper boundary of our region, y equals 1 divided by x. If you think about how this region would be revolved around the x-axis to form the solid of revolution, this curve or this boundary would be the outer radius. It's the curve on the outside of the washers or the disks that would be created that make up the solid of revolution. Okay, so that is our outer radius, and then the inner radius would be that lower boundary for the region, which is y equals 0, or essentially the x-axis. And so since that inner radius is just the axis of revolution, it's going to be equal to 0, okay? This volume will be equal to pi times the integral from a lower bound to an upper bound, which I'll come back to in a second, but then inside the integral, we'll have that outer radius squared, so 1 divided by x will be squared, and then we're subtracting the inner radius of 0 squared. Okay, so our initial setup here is for the washer method, where you have an outer and inner radius, but since that inner radius is 0, technically we would just be using the disk method here. Okay, but we still have to account for these bounds of integration. So what values of x does our region lie between? Well, it's going to have a lower bound of x equals b and an upper bound of x equals 2. Okay, so x equals b is the lower bound and x equals 2 is the upper bound. And so now we're almost done. This would be a fine setup if we were going to calculate the volume, but remember that in this specific problem, we have been given the volume and we want to solve for one of those bounds of integration. Okay, we want to know what the value of b is when the volume is 3. So we are going to set 3 equal to that integral. All right, and so that's our setup. Now we just need to work on evaluating the integral and getting it to a point where we can solve for b. So let's do that. Beginning by rewriting this integral a little bit, or by simplifying it, we'll have 3 is equal to pi times the integral from b to 2 of 1 divided by x squared, which will just be 1 divided by x squared, and then dx, because we are subtracting 0. So this is the only expression left in the integral. Okay, now to integrate 1 divided by x squared, perhaps it would be easier if we rewrote it by moving x squared to the numerator, by making its exponent negative. That way we can see how to use the power rule for integration. So that would look like this. We'd have 3 is equal to pi times the integral from b to 2 of x to the power of negative 2 dx. And then using the power rule for integration, you want to add 1 to that exponent and then divide by that new exponent. So negative 2 plus 1 is negative 1, and then you want to divide by negative 1. So that will give you that 3 is equal to pi times negative x to the power of negative 1, evaluated from b to 2. Okay, again, negative 2 plus 1 is negative 1, so you have x to the power of negative 1, and then dividing by negative 1 gives you negative x to the power of negative 1. Okay, so then continuing our work up here, we have 3 is equal to pi multiplied by -1 divided by x, evaluated from b to 2, right? If you take x to the power of -1 and move it to the denominator, you just have 1 divided by x to the first power. And now let's evaluate that at 2 and subtract the evaluation at b. And by the way, this was not an improper integral. That's something that you do want to be on the lookout for, but this is not an improper integral because that lower bound of b cannot be 0, right? If it could be 0, then this would be a problem because the integrand 1 divided by x squared is not defined at x equals 0. But as we know, b is between 0 and 2, so we're not in any danger there. We don't have to introduce a limit or anything like that. Okay, so we are fine to evaluate like this, but then plugging 2 into this expression and plugging in b, we find that 3 is equal to pi times -1/2 minus -1 divided by b. Okay, don't forget that you are subtracting a negative expression, so you need both of those negatives, which will cancel out, so you'll have 3 is equal to pi times -1/2 plus 1 divided by b. Okay, and now at this point, our goal is to solve for b. We've done the integration. Now we need to solve for that value of b such that the volume is 3. Okay, so to do that, let's begin by distributing pi through this quantity, giving us 3 is equal to -pi divided by 2 plus pi divided by b. And then let's add pi divided by 2 to both sides of the equation. So we get 3 plus pi divided by 2 is equal to pi divided by b. And then let's multiply both sides of the equation by b. So we have b times 3 plus pi divided by 2 is equal to pi. And then our last step is to divide both sides of the equation by this quantity, which will then isolate and solve for b. So doing that, we find that b is equal to pi divided by 3 plus pi divided by 2. That is the final answer to this problem. It's a weird value for b, but if you put it into a calculator, it's approximately equal to 0.6873 and some more decimals, which does make sense. Remember that b is between 0 and 2, and that decimal value is between 0 and 2, so it does make sense. There's no issues there, but as an exact value, it's pi divided by 3 plus pi divided by 2. That is the value of x where this line would need to be such that this region revolved around the x-axis would create a solid of revolution with a volume of 3. Okay, so that's it for this problem. Let's move on to the next one. For our third review problem, we want to evaluate the integral, and we're given the integral from 0 to 5 of 10 divided by x dx. Okay, so at first glance, this seems to be a pretty innocent integral, right? It looks like something you might have done in Calculus 1, except it's not, because something that you want to be on the lookout for here in Calculus 2, especially on your final exam, are any integrals that are improper integrals. And while most improper integrals are pretty obvious because they'll have a bound that is infinity or negative infinity, don't forget that improper integrals are also a thing when the function in the integrand is not defined for a value that you are integrating over, right? In this case, we are integrating from 0 to 5, but 10 divided by x is not defined at x equals 0. Because if x equals 0, you have 10 divided by 0, which is an undefined value. You can't divide by 0. So what we have here is an improper integral, and so we need to treat it as such. What we need to do is introduce a limit. We need to replace that lower bound of 0 with a variable that we will then introduce a limit for. Okay, so that will look like this. We will say that this integral is equal to the limit as a, I'm going to let the lower bound be equal to a, as a approaches that lower bound of 0, specifically from the right, since we are replacing the lower bound, we will be looking from the right as opposed to the left. If we were replacing the upper bound, we would be looking at the limit from the left, but since we are replacing the lower bound, and it's a finite value of 0, we do have to look from the right, but then you have the integral from a to 5 of 10 divided by x dx. Okay, so all I did here was replace that lower bound of 0, where the function was undefined, with a, and then introduce the limit as a approaches that lower bound of 0 from the right. Everything else in the integral is the same. But now we're good to go. We can work on evaluating this integral, and then eventually the limit. And the first thing I want to do here is pull out this constant of 10. So this would be equal to the limit as a approaches 0 from the right of 10 times the integral from a to 5 of 1 divided by x dx. Okay, now it's a little bit easier to see what we can do to integrate this expression. We know that the integral of 1 divided by x is the natural log of the absolute value of x. So what we get next here is the limit as a approaches 0 from the right of 10 times the natural log of the absolute value of x evaluated from a to 5. Okay, so then continuing my work up here, we want to evaluate this expression at 5 and subtract the evaluation at a. And so that will look like this. We have the limit as a approaches 0 from the right of 10 times the natural log of 5. You don't need absolute value bars for that because 5 is a positive value. So you have the natural log of 5 minus the natural log of the absolute value of a. And really, we don't need the absolute value bars around a either, because for the limit, we are looking at a as it approaches 0 from the right, which are all the positive values leading up to 0. So we can rewrite that as well and have the natural log of a. No absolute value bars required. But now, we are at a point where we can evaluate this limit. It is a one-sided limit, but we can still plug in the value that a is approaching into this expression and see what we get for the limit. So if we do that here, we'll have 10 times the natural log of 5 minus the natural log of a, but now we're going to plug in 0 for a to evaluate the limit. So we have the natural log of 0. But the natural log of 0 is an undefined value, right? If you were to look at the graph of the natural log function, it looks something like this. You have a curve that will never touch the y-axis, where x is equal to 0, so the function is not defined for that value, x equals 0. So technically, we can't evaluate the limit like this. We really can't plug 0 into the natural log function, but we can do something else. Remember that we are looking at the limit as a approaches 0 from the right, and so if we look at the natural log function, as the input values approach 0 from the right, meaning from this direction, as we approach x equals 0 from the right, the output values, or the y values, progressively get smaller and smaller in the negative direction. In other words, we're approaching negative infinity. That is what we would get for the limit as a approaches 0 from the right of the natural log of a. So taking that into account, we now have 10 times the natural log of 5 minus the natural log of a, which we have just determined for this limit is equal to negative infinity. And so simplifying, these two negatives will cancel out, giving you 10 times the natural log of 5 plus infinity. And so we have a finite value of the natural log of 5 plus infinity. This is practically nothing compared to infinity, so adding it to infinity doesn't really change anything. This entire value would just be infinity, so we have that this is equal to 10 times infinity. But again, if you multiply 10 by infinity, you're still going to have infinity. You still have a positive infinite value. Okay, so 10 times infinity is equal to infinity, which would be our final answer for this integral. But what this means is that the area under this curve from 0 to 5 does not converge to a single value. This improper integral is divergent. Okay, so you want to make a note of that as well. If you get an infinite result for an improper integral, you want to write down that infinite value, but then also make a note that it is divergent. Okay, and that would be the final answer for this problem. Let's move on to the next one. For our fourth review problem, we want to find the area of the region inside the circle r equals 3, but outside the cardioid r equals 1 plus cosine theta. Okay, so in this problem, we're working with calculating polar area, or area in polar coordinates, specifically the area between two curves. So before we set up any calculations, let's start by drawing a picture of the region that we want to find the area of. So here's my vertical axis, and here's my polar axis. Remember that this is an angle of 0, this is an angle of pi divided by 2, this is an angle of pi, and this is an angle of 3 pi divided by 2. Okay, now our first curve here is a circle represented by r equals 3, so that's just a circle with a radius of 3. So a radius of 1, 2, 3 takes us right here in this direction. It also takes us 1, 2, 3 in this direction, 1, 2, 3 in this direction, and 1, 2, 3 in this direction. Okay, so then our circle, represented by r equals 3, would look like this. Okay, so that's one of our curves, but then for the other one, we have the cardioid r equals 1 plus cosine theta. And so if you don't remember what the graph of this polar equation looks like, you could plug in some different angles of theta and get the corresponding radius values, and that will give you some points that you could plot in the polar coordinate system that you could then connect to get the graph of the cardioid. Hopefully you do remember though that a cardioid means a curve that is sort of in the shape of a heart. It's one of our different kinds of limacons that can be represented by a polar equation. But we're not trying to make a perfect graph here. We're just trying to sketch our region so that we have an idea of what kind of integral we're going to set up to calculate the area of that region. Okay, so what I'm going to use here are some little shortcuts for quickly graphing a cardioid of this form. I show these in my lesson video for graphing polar equations, but when you have r equal to some constant plus or minus a constant times cosine theta, it represents a cardioid of this form. Or really, this is for when you have a plus b. If you have a minus b, then this graph gets flipped about the vertical axis. You would have a cardioid in the opposite direction, but you don't have to worry about that here. We do have 1 plus cosine theta. So our values of a and b in this case are 1 and 1, right? B is the coefficient of cosine, and there is nothing there, so we know it's 1. So since a is equal to 1 and b is equal to 1, in our case, we know that the graph of that cardioid is going to start at the origin, but then cross through a radius of 1 above the polar axis and below the polar axis, and the cardioid will reach out to a radius value of a plus b. So 1 plus 1 is 2, right? A plus b equals 1 plus 1, which equals 2. So here are the points that we can plot to help us graph this cardioid. We'll have a point at the origin, and then a point at a radius of 1 above the polar axis, a point at 1 below the polar axis, and then a point at a radius of 2 along the angle of 0. Okay, and so then connecting those points, making the shape of a cardioid, we get something like this. Okay, again, it's probably not a perfect sketch, but it's going to be good enough for our purposes here, because now we can clearly see the region that we're working with in this problem whose area we want to find, right? We have this circle r equals 3, and then this cardioid, I'll also write that right down here. This is r equals 1 plus cosine theta, and we want to find the area of the region inside the circle, but outside the cardioid. Okay, so we're going to be working with area inside this circle, but not inside this cardioid. We want to work with the area outside of it. So the region that we want to calculate the area of looks like this if I shade it in. I'll label that region with a capital R. But then to calculate the area of that region, we need to set up an integral that will calculate the area between two polar curves. And the formula that we use for that looks like this. The area of that region will be equal to 1/2 times the integral from alpha to beta, where those are two angles of theta, and then we have the outside curve, which is represented by some function in terms of theta, which will be squared, and then we subtract the inside curve, which is represented by a different function in terms of theta, and that is also squared, and then don't forget about d theta. All right, so as a quick reminder, remember that the area underneath one polar curve looks like this. The area is equal to 1/2 times the integral from alpha to beta of the function in terms of theta, or r squared times d theta. But since we want to find the area between two polar curves, we have to take the difference between the outer curve squared and the inner curve squared. Okay, and I write f of theta and g of theta to distinguish between those two curves represented with r. Okay, so that's what we're working with here. But now let's set it up. Let's set up this integral to calculate the area of this region. We will have that the area is equal to 1/2 times the integral between what two values of theta? Well, this region that we have here starts at an angle of 0 and then makes its way all the way around the polar coordinate system back to that angle of 0, or what we would call 2 pi, right? A full circle takes you from 0 to 2 pi. So those will be our bounds of integration. We will integrate from 0 to 2 pi. Okay, these two curves do not intersect anywhere. You just want to look at the graph visually to determine what two angles of theta to integrate between. All right, but then filling in the rest of our integral, f of theta is going to be our outside curve, which is r equals 3. So we will square 3 and then subtract squaring the other curve, the inside curve, which is r equals 1 plus cosine theta. So we'll take that quantity, 1 plus cosine theta, and square it, and then write d theta. Okay, so that's the setup. This is the integral that will calculate the area of this region. Now let's work on evaluating it. The first thing I want to do here is square 3 and square this quantity of 1 plus cosine theta, because currently we cannot integrate this expression. We have to simplify it and manipulate it a little bit into a form that we can integrate. Okay, so this is equal to 1/2 times the integral from 0 to 2 pi of 9 minus this quantity squared. And I'm going to use a trick here to square it quickly. Remember that if you want to square a quantity with two terms, to do it quickly, you square the first one, then add that to multiplying the two terms together, but multiplied by 2, and then add that to the second term squared. So doing that here, 1 squared is 1, then 1 times cosine is just cosine, but then multiply it by 2, so you get 2 cosine theta, but then you want to add that to cosine theta squared, which will give you cosine squared theta. All right, and now you want to distribute this negative through this quantity. So you'll have -1, -2 cosine theta, and negative cosine squared theta. But notice that the 9 and -1 would both be constants that can be combined. They are like terms, which would give you 8. So what we get next is 1/2 times the integral from 0 to 2 pi of 8 minus 2 cosine theta minus cosine squared theta. All right, and so now the next thing we want to do here is split up this integral, right? We have 3 different terms that are all going to be integrated differently. So let's just split up the integral so that we can work on each of them separately. If we split up the integral, we will get 1/2 times the integral from 0 to 2 pi of 8 d theta plus 1/2 times the integral from 0 to 2 pi of -2 cosine theta d theta plus 1/2 times the integral from 0 to 2 pi of negative cosine squared theta d theta. Okay, now simplifying things a little bit here, you can pull this 8 to the front of this integral, and 8 times 1/2 is 4. So we get 4 times the integral from 0 to 2 pi times d theta. So we're just integrating 1 there. That's a pretty nice integral. We'll come back to that though. I then want to pull out this -2 to the front of this integral. -2 times 1/2 is -1. So we'll just be subtracting this integral from 0 to 2 pi of cosine theta d theta. And we know how to integrate cosine. The integral of cosine is sine. So that's another nice integral. It's just going to be this last one that's a little bit more difficult. I'm going to pull that negative out front. So we will have -1/2 times the integral from 0 to 2 pi of cosine squared theta d theta. And what we have here is a trigonometric integral where we will need to make use of a trig identity. And so we'll set that up in just a second. Let's move on to the next step and work a little bit on these two integrals. The integral of 1 is theta, so this will be equal to 4 times theta evaluated from 0 to 2 pi. And then we are subtracting the integral of cosine theta, which is sine theta. So we'll have sine of theta evaluated from 0 to 2 pi. And now let's rewrite this integral. The identity that we're going to use here is that cosine squared theta is equal to 1/2 multiplied by 1 plus cosine of 2 theta. Okay, so rewriting the integral here, we'll have -1/2 times the integral from 0 to 2 pi of 1/2 times 1 plus cosine of 2 theta d theta. Okay, I just replaced cosine squared theta with this expression from this trig identity. And by doing that, we now have an expression that we can actually integrate. We can't really integrate cosine squared theta on its own, but rewriting it like this puts it in a form that we can integrate. And I am going to pull this 1/2 out to the front, multiply it by -1/2, and you'll get -1/4. That'll just make our life a little bit easier in the next step, because what we're going to want to do is then split up this integral into 2 pieces so that we can integrate 1 and cosine of 2 theta individually. Okay, so moving on to our next step, let's start over here. this will be equal to 4 times theta evaluated at 2 pi minus the evaluation at 0. So we're just replacing theta with 2 pi and then subtracting, replacing it with 0. So you have 2 pi minus 0, which is 2 pi, times 4, which just gives you 8 pi. So I'll write in 8 pi. And then we are subtracting sine evaluated at 2 pi minus sine of 0. So we have sine of 2 pi minus sine of 0. But sine of 2 pi is 0, and sine of 0 is 0. So you have 0 minus 0, which is 0. And so this whole thing just becomes 0. We actually don't get any significant value from that part of this integral. So we have 8 pi minus 0, and then we have this integral to take care of, which I am now going to split up into two pieces. We'll have minus 1/4 times the integral from 0 to 2 pi of 1 d theta, and then minus 1/4 times the integral from 0 to 2 pi of cosine of 2 theta d theta. All right. Now for this integral, we're just integrating 1, which is pretty nice. But for this one, we have cosine of 2 theta, which technically does require the use of u substitution. You would want to set u equal to that inside function of 2 theta. But if you're familiar with how that process works, really all that's going to change from that is you'll end up with sine of 2 theta, but then divided by 2, or multiplied by 1/2. Okay, so if you know that shortcut, if you've done this integral enough times to skip right to that, go for it. But just for the sake of clarity, I am going to show the u substitution here. So let's work on that. We will have that this is equal to 8 pi, and we don't need to rewrite minus 0, but then we do have minus 1/4 times the integral of 1 d theta, which is just theta. So we have theta evaluated from 0 to 2 pi, and then we have minus 1/4 times this integral, where I will now use u substitution. We're going to let u equal 2 theta, and so the derivative of u with respect to theta is 2, right? The derivative of 2 theta is 2, if theta is a variable that we're taking a derivative with respect to. And so then solving for du, we get du equals 2 d theta. But in the integral, I only see d theta. I don't see a 2. So let's divide out that 2, and we get du divided by 2 equals d theta. Okay, so rewriting the integral in terms of u, except for the bounds, because we are going to go back into terms of theta. We have the integral from theta equals 0 to theta equals 2 pi. If you wanted to, you could change those to be in terms of u, but I'm not going to here. We will have cosine of u times d theta, which is now du divided by 2. Okay, so then that 1/2 you can pull out to the front and have negative 1/8. That's what I'm going to do here. We have cosine u du, and then out front here, we have negative 1/8. And then you can integrate cosine of u to get sine of u, and then replace that u with 2 theta. Okay, so here's what we get next. This is equal to 8 pi minus 1/4 times theta evaluated at 2 pi minus the evaluation at 0, which will just give you 2 pi. And then we have minus 1/8 times the integral of cosine u, which will be sine u. But again, remember that u is equal to 2 theta, so just replace that, substitute it back in, and you'll have sine of 2 theta evaluated from theta equals 0 to theta equals 2 pi. All right, and so we're almost done. This is going to simplify pretty nicely. 1/4 times 2 pi is pi divided by 2, so this is equal to 8 pi minus pi divided by 2, minus 1/8 times sine of 2 theta evaluated at 2 pi minus the evaluation at 0. But sine of 2 theta evaluated at 2 pi will be sine of 4 pi, and sine of 4 pi is 0, and sine 2 theta of 0 will be sine of 0, which is also 0. So you're just going to get 0 for this term, which means you have negative 1/8 times 0, and that whole term just becomes 0. So the final answer here will just be 8 pi minus pi divided by 2, and 8 pi in terms of halves would be 16 pi divided by 2. So 16 pi divided by 2 minus pi divided by 2 gives you the final answer of 15 pi divided by 2. That is the value for the area of the region inside the circle r equals 3, but outside the cardioid r equals 1 plus cosine theta. Okay, and by the way, since this is a value of area, technically you could include units here, it would represent an amount of units squared. So if you want to write down square units, you can. That might be a preference thing, but just remember that we did find area here, so it does represent an amount of square units. But with that, that is it for this problem. We found the area of that region, and so we're done. For problem 5, we want to evaluate the integral, and we have the integral of tangent cubed x dx. Alright, so what we have here is a trigonometric integral, specifically one that only involves tangent, but whether the trig integral involves both tangent and secant, or sine and cosine to different powers, or just one of those trig functions to a power, the general process remains the same. Whenever you see an odd power for your trig function, you want to split that up. You want to rewrite it where you have a trig function to the power of 1 multiplied by that trig function to an even power. And so in this case, we have tangent cubed x, which means we want to split it up into tangent to the first power times tangent squared. Right, so our first step here is to rewrite the integral like this. We'll have tangent squared x times tangent x dx. Okay, tangent squared x times tangent x is still equal to tangent cubed x. Both represent the same expression, we're just writing it in a different way. And the reason we do this is because then we can rewrite the integral using a trigonometric identity that will then give us a way to actually solve the integral. Because in its current state, we have no idea how we would integrate this expression. Right, we don't have a simple rule for integrating tangent cubed x, and writing it in this way doesn't initially make it any easier either. But what will make it easier is if we rewrite tangent squared x using the Pythagorean identity for tangent and secant. Right, remember that tangent squared x is equal to secant squared x minus 1. Or sometimes you'll remember it as tangent squared x plus 1 is equal to secant squared x. Either way, it's the same identity. It is the Pythagorean identity for secant and tangent. But what we want to do is replace tangent squared x in this integral with this expression. So let's do that here. Our next step is to replace tangent squared x with secant squared x minus 1 times tangent x dx. Okay, but now we will need to make some more adjustments here, because although this is getting us closer to an integral that we actually know how to solve or how to integrate, it's not quite there yet. At this point, if you're thinking about your different integration techniques, u substitution really wouldn't work here, because whatever you set u equal to, its derivative also needs to be within the integral. And while the derivative of tangent is secant squared x, so you might be tempted to set u equal to tangent x and use u substitution, but you have to also account for this negative 1 right here. The secant squared x has to be on its own, right? You would have to have secant squared x times tangent x in order for you to use u substitution. These two terms are attached to one another, creating their own quantity. You can't let u be equal to tangent x and then replace this quantity with du. It doesn't work like that. Okay, so you can't use u substitution here by setting tangent equal to u. You also couldn't set secant x equal to u because the derivative of secant is secant times tangent, and that's not really in this integral either. So in its current form, we can't use u substitution on this integral, and you can't really use integration by parts either. So what do we do here? Well, why don't we just try distributing tangent x through this quantity? If we do that, we get the integral of secant squared x times tangent x minus tangent x. And then we still have dx. Okay, so I multiplied tangent x by secant squared x. So we have secant squared x times tangent x. And then I multiplied tangent x by negative 1 to get negative tangent x. And now we have two separate terms within this integral that we could integrate individually, right? We could split up this integral into two integrals, one for this term, and then you'll subtract an integral of this term, and both of those will be integrals that we can solve. So let's work on that here. I'll continue my work up here, and we will have the integral of secant squared x times tangent x dx minus the integral of tangent x dx. Okay, and so now that we've split it up, we can work on each of them separately, and notice that for this integral, we could now use u substitution, because if you set u equal to tangent x, the derivative of tangent is secant squared x, and that's all that we have here in the integral. Okay, that negative 1 from before is no longer there, so we don't have to account for it. It's not going to cause us any issues. So we can use u substitution on this integral, And then for the integral of tangent x, there's actually a rule for that you do learn in Calculus 1. We know that the integral of tangent x is the negative natural log of the absolute value of cosine x. But if you didn't have that memorized, you could also use u substitution to solve this integral as well. You just have to rewrite tangent in terms of sine and cosine. So I'll do that here just to show you the full work in case you don't remember that integration rule. But certainly knowing it does save you some time. But let's go through all the steps here. I'm going to use u substitution on this integral. I'm going to let u be equal to tangent x. So du dx, or the derivative of u with respect to x, is secant squared x. And so then solving for du is equal to secant squared x dx. Okay, I just multiplied both sides of the equation by dx. So then rewriting this integral to be in terms of u, we find that it's equal to the integral of just u du. Right? We replaced tangent x with u because that's what we set it equal to, and we replaced secant squared x dx with du because that's what we found that was equal to. All right, and then we're going to subtract the integral of tangent x dx. Again, if you do know the integration rule, you could just use it here, but I'm going to show you the other way of doing this in case you don't remember the integration rule for tangent, because you don't use it a whole lot, but you want to rewrite tangent x in terms of sine and cosine. And we know that tangent is equal to sine x divided by cosine x. So we have sine x divided by cosine x dx, and then we can use u substitution on this integral by letting u equal cosine x, and then the derivative of cosine is negative sine, so that will work out. Okay, now just to avoid any potential confusion, we did already use u for the u substitution of this integral, so let's use a different variable here. I'll use w, so I'm going to let w be equal to cosine x, and so then dw dx, or the derivative of w with respect to x, will be the derivative of cosine, which is negative sine. All right, and then solving for dw, we get dw is equal to negative sine x dx. Okay, and you can keep it like that because technically we do have a negative sign right here that can be replaced. So we will replace negative sine x dx with dw, so then this integral will become positive. Okay, but here's what we end up with. Integrating u, you want to use the power rule for integration. So add 1 to the exponent and then divide by that new exponent, and you will get u squared divided by 2. Or if you want to pull that 1/2 out front, you can write it as 1/2 times u squared. And then that will be added to this integral, and it is a plus sign now because we're going to replace negative sine x dx with positive dw, but we have the integral of 1 divided by cosine x, which is now w, so we have 1 divided by w dw. All right, and so then rewriting this first term here, we want to get u back into terms of x, and we let u be equal to tangent x, so this is equal to 1/2 tangent squared x. Right, u is being squared, so you want to square tangent as well. But then that will be added to the integral of 1 divided by w dw, which is the natural log of the absolute value of w. So we get the natural log of the absolute value of w, and at this point we can add on the constant of integration c, so write in plus c, and then our final step is to replace w with what we set it equal to for that u substitution, or I guess in this case, w substitution. But either way, our final answer becomes 1/2 times tangent squared x plus the natural log of the absolute value of cosine x plus c. That right there is the answer to this integral. Okay, and once again, if you know that the integral of tangent x dx is the negative natural log of the absolute value of cosine, then you can go right from this step to this step if you'd like. That is fine. I just wanted to show you the steps here of where that comes from. But with that, that is it for this problem. Let's move on to problem 6. And for problem 6, we want to find dy dx and d squared y divided by dx squared at t equals pi for the given parametric curve without eliminating the parameter. And we have x equals 3 times sine of 3t and y equals cosine of 3t, where t is between 0 and 2 pi. Okay, so these two equations right here that we've been given are the parametric equations that represent a particular parametric curve. And what we need to do is find the first and second parametric derivatives for those parametric equations without eliminating the parameter. Okay, so we are not supposed to rewrite these parametric equations as a rectangular equation and then take its derivative. We want to find the derivative using the parametric equations as they are. Okay, and so to find a parametric derivative, remember that the formula looks like this. We know that dy dx is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. All right, so let's set this up here. Let's start with the derivative of y with respect to t. So we're going to be taking a derivative of our parametric equation for y that is expressed in terms of t. And so we have cosine of 3t, and the derivative of cosine is negative sine, but since this is a composite function, meaning the inside function is not just t, it's 3t, we need to use the chain rule and multiply by the derivative of that inside function. Okay, so again, the derivative of the outside function, keeping the same inside function, will produce negative sine of 3t, but don't forget to then multiply by the derivative of that inside function. And the derivative of 3t with respect to t is 3. Okay, so that's dy dt, but now let's find dx dt. We need to take the derivative of x with respect to t, and we have 3 times sine of 3t, and we will have to use the chain rule here again because we have sine of a function other than just t, right? It's 3t. So take the derivative of the outside function first. The derivative of sine is cosine. So you'll still have that 3 on the outside multiplied by cosine of the same inside function, 3t, but then you need to multiply by the derivative of that inside function. And again, the derivative of 3t is 3. Okay, so that's dx dt, which means we have now set up dy dx. We now just want to simplify it, and notice that we have these common factors of 3 in the numerator and denominator that will cancel out. And then also notice that we have sine of 3t divided by cosine of 3t. Whenever you have sine divided by cosine, and they both are of the same angle, or they both have that same inside function, you can just rewrite that as the tangent function with that inside function. Okay, we just used this trig identity in the previous problem. We know that tangent is equal to sine divided by cosine. So here's how we can simplify this. We'll still have negative 1/3 on the outside, right? Negative 1/3. But then we're going to rewrite sine of 3t divided by cosine of 3t with just tangent of 3t. That is an easier way to express that parametric derivative. Okay, so that right there is the parametric derivative, dy dx. But we're not done yet. We still want to find the second derivative as well, and we also want to evaluate both of them at t equals pi. Okay, so let's actually do that first. Let's take dy dx and evaluate it at t equals pi. So we're going to plug in pi for t in this expression. So that will be equal to negative 1/3 times tangent of 3t, where t is pi, so we have 3 pi. Okay, and tangent of 3 pi is equal to 0. So you have 0 times negative 1/3, which is just equal to 0. Okay, so that is the evaluation of dy dx at t equals pi. And so that takes care of the first derivative. But now let's work on the second derivative. We want to find d squared y divided by dx squared. And so remember, to find the second parametric derivative, what you do is you take the derivative with respect to t of the first parametric derivative, dy dx, and you divide it by dx dt, or the derivative of x with respect to t, the same exact expression that was in the denominator of dy dx. Okay, so let's set this up. We're going to take the derivative with respect to t of dy dx, which we found earlier. So we're going to write in negative 1/3 times tangent of 3t, and then that will be divided by dx dt, which we already found earlier. It was 3 cosine of 3t times 3. So if you multiply those 3's together, you get 9 times cosine of 3t. All right, now let's take the derivative with respect to t of dy dx, and we will have to use the chain rule here because you have tangent of 3t. So the inside function is 3t, and the outside function is tangent, and the derivative of tangent is secant squared. So this is equal to negative 1/3 times secant squared of 3t. That's the derivative of the outside function. You keep that same inside function, but then multiply that by the derivative of the inside function. And the derivative of 3t is 3. So we multiply by 3. And then that is still divided by 9 cosine of 3t. All right, now something nice that happens here is that this 1/3 will cancel out with this 3. 1/3 times 3 is just 1, but that negative stays there. That negative is not gone. And at first, that seems like the only thing that we can really simplify here, but we can make this second derivative a little bit nicer, because remember that secant is equal to 1 divided by cosine, right? Another trig identity is that secant theta is equal to 1 divided by cosine theta, or whatever that angle happens to be. In this case, it's 3t. Okay, so if we have cosine of 3t in the denominator here, essentially 1 divided by cosine of 3t, you can rewrite that as secant of 3t. And you'll be able to multiply that into the numerator and combine it with this secant squared right here. Okay, so let me show you what I mean by that. Continuing my work down here, this will be equal to negative 1/9, and that will be multiplied by secant squared of 3t, which will then be multiplied by another secant of 3t, because I'm rewriting 1 divided by cosine of 3t as secant of 3t. So writing that in here, we can then multiply these two expressions together and get negative 1/9 times secant cubed of 3t. Okay, so I'm actually going to write that right here. Our final answer for d squared y divided by dx squared, or the second parametric derivative for these parametric equations, is negative 1/9 times secant cubed of 3t. Okay, that is the final answer for the second parametric derivative, but we're not quite done yet. We still need to evaluate that at t equals pi, so let's do that yet. If you evaluate d squared y divided by dx squared at t equals pi, we will get negative 1/9 times secant cubed of 3 pi, right? We're replacing t with pi. And secant cubed of 3 pi would be the same as secant of 3 pi quantity cubed. So whatever secant of 3 pi is, we're just going to cube that. And secant of 3 pi is negative 1. So this is equal to negative 1/9 times negative 1 cubed. And negative 1 cubed is negative 1. So we'll have negative 1 times negative 1/9, which will just be equal to positive 1/9. And so positive 1/9 is the evaluation of the second parametric derivative at t equals pi. And with that, we have now finished this problem. We found both the first and second parametric derivatives and evaluated them at t equals pi. Next up, for problem 7, we want to let R be the region enclosed by y equals x, y equals 8x, and y equals 4. And then we have two parts to consider. For part A, we want to compute the area of R by evaluating an integral or integrals in terms of x. And then for part B, we want to compute the area of R by evaluating an integral or integrals in terms of y. Okay, so in both cases, we're going to be calculating the area between some curves, or really in this case, we're working with lines, but we'll get to that in a second. But we're going to take turns finding that area in terms of x and then in terms of y. So before we do anything here, before we try to set up any integrals, I think it's very important that we graph these different lines that we've been given and get a visual of the region that we're actually trying to calculate the area of. All right, so I'm going to draw a y-axis here, as well as an x-axis. And our first line is y equals x, which is a line that is simple enough to graph. I'll let y equals x be represented by this line right here. It's just a line that has a slope of 1 that passes through the origin. So that is y equals x. And then we have y equals 8x, which is also a line that passes through the origin, but it will have a slope of 8. Okay, so if this is y equals 1, 2, 3, 4, 5, 6, 7, 8 right here, and then this is x equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Right, but this over here is x equals 1. That's the important thing I want to mark here. Then a line with a slope of 8 would rise up 8 units and then run 1 unit. Okay, so this point right here will be on that line. So I'm just going to connect the origin to that line to create the graph of y equals 8x. That will end up looking like this. Again, that is y equals 8x. And then we also have y equals 4. And so that will be a horizontal line that crosses through y equals 4 along the y-axis. So this is y equals 1, 2, 3, 4 right here. And through that y value, we will have the line y equals 4. Okay, so that's y equals 4. which means that the region that we want to calculate the area of here is this region right in here, this triangular region that is enclosed by these 3 lines. And something that's going to be helpful for us to identify before we set up any of the integrals that are going to calculate the area of this region are those points of intersection between y equals 4 and these 2 lines. Now, I drew a pretty good sketch here, so I can visually identify those points. I can see that this point right here is x equals 4 and y equals 4. So that right there is the point 4, 4. And then this point over here, I can see would have an x coordinate of 1/2 and a y coordinate of 4. Okay, now I'm doing that visually, but if you could not see that because your graph is not as accurate or you just want to be sure, you can always figure out what those points of intersection are by setting the lines equal to each other. Okay, so if you want to know where y equals 4 intersects with y equals 8x, set 4 equal to 8x, and then solving for x will give you 1/2. So the x coordinate of that point is 1/2. Okay, we know it's y equals 4 because this is the line y equals 4 right here. Obviously, the y coordinate of that intersection has to be y equals 4, but we're just solving for that x coordinate. And then the same thing for this point right here. If you set 4 equal to x, then very clearly the x coordinate has to be 4 for that point of intersection between those 2 lines. Okay, so I just wanted to make that clear. That's where those coordinates are coming from. And do also notice that these 2 lines, y equals 8x and y equals x, intersect each other at the origin. That's an easier point to identify. That is very clearly 0, 0. But now that we have identified those points of intersection, we are ready to begin setting up some integrals to calculate the area of this region. And so let's start with part A. We want to compute that area by evaluating an integral or integrals in terms of x. And so remember, when you want to calculate the area between 2 curves, or in this case, 2 lines, and you want to work in terms of x, you want to look from the top down when identifying your top function and your bottom function. Okay, because remember, the formula looks like this. The area is equal to the integral from a to b of the top function, so f of x, minus the bottom function, which I'll call g of x. Okay, so that is how we calculate the area between 2 curves, f of x and g of x. And so looking at our region here, what would be our top function and bottom function? Well, at first glance, it looks like that this line y equals 4 is going to be the top function, right? That looks to be the boundary for the top of the region, but it actually doesn't account for the entire region, right? This region, it starts from x equals 0 to x equals 4, but this line y equals 4 is not the top function for all of those values of x. It's the top function from x equals 1/2 to x equals 4. There's this little section right here where y equals 8x is the top function. Okay, from that point of intersection, you could draw a line downwards and see the 2 different parts of this region where there is a different top function. The bottom function remains the same, right? It's y equals x the whole way through from x equals 0 to x equals 4. But from x equals 0 to x equals 1/2, the top function is y equals 8x. And then after that, from x equals 1/2 to x equals 4, the top function is then y equals 4. So because the top function does not remain the same, because it changes throughout the region, we can't calculate the area of the region with just one integral. We have to use 2 integrals. We have to split up this area calculation into 2 parts. We'll calculate the area of this little piece right here, and then we'll calculate the area of this piece. Okay, so let's set that up here. The area in terms of x will be equal to the integral where we calculate the area of the first piece from x equals 0 to x equals 1/2. So we go from 0 to 1/2, where the top function is 8x. So we will have 8x minus the bottom function, which is going to be y equals x. So just write in x, and then that will be multiplied by dx. That is the area of that first little piece. Now let's add that to another integral that will account for the other piece of the region. We'll have the integral from 1/2 to 4. That accounts for the values of x from here to here, where y equals 4 is now the top function. So we will have 4 minus that bottom function of x, and that will be multiplied by dx. Okay, so now we have the 2 integrals set up. Now let's solve them. I want to start by simplifying this integral. 8x minus x is just 7x. So we can pull that 7 out to the front and have that this is equal to 7 times the integral of x dx from 0 to 1/2, and then that will be added to the integral from 1/2 to 4 of 4 minus x. Now the integral of a constant will be that constant times the variable of integration. So we will have 4x and then minus the integral of x. So add 1 to the exponent, divide by that new exponent, and you get 1/2 x squared. And again, that is evaluated from 1/2 to 4. All right, and then let's integrate x. This will be equal to 7 times 1/2 x squared, evaluated from 0 to 1/2. And then let's evaluate this expression at 4 and subtract the evaluation at 1/2. So we will have plus 4 times 4 minus 1/2 times 4 squared. That's the evaluation of this at 4. And then let's subtract the evaluation at 1/2. We'll have 4 times 1/2 minus 1/2 times 1/2 squared. Okay, and so simplifying further, we need to evaluate 1/2 x squared at 1/2 and then subtract the evaluation at 0. So this will be equal to 7 times 1/2 times 1/2 squared minus 0, right? If you plug 0 into this expression, you will just get 0. And then that will be added to this over here. 4 times 4 is 16. So we have 16 minus 1/2 times 4 squared. 4 squared is 16, times 1/2 is 8. So we have 16 minus 8, which is just 8. So I'm going to rewrite that as just 8. And then we are subtracting 4 times 1/2, which is 2. So we have 2 minus 1/2 times 1/2 squared. 1/2 squared is 1/4. 1/4 times 1/2 is 1/8. So we have 2 minus 1/8. And then a very similar simplification over here. 1/2 squared is 1/4. 1/4 times 1/2 is 1/8. 1/8 minus 0 is still 1/8. And then multiplied by 7 gives you 7/8. And that will be added to this expression. 2 minus 1/8 will result in 15/8 because 2 would be the same as 16 divided by 8 or 16/8. So subtracting 1/8, you get 8 minus 15/8. And so then adding the fractions will give you negative 8/8, which is negative 1. So you get 8 minus 1, which is equal to 7. So 7, and that is a measurement of area, so remember that the units would be squared, but 7 is the area of this region. Okay, we just calculated it in terms of x, which required using two integrals. That was for part A, but now for part B, we want to calculate that same area, but now working with an integral or integrals in terms of y. So if our work here is correct, our answer should be the same. When we calculate the area in terms of y, we should also get 7 because we're still calculating the area of this same region, we're just taking a different approach. And as you're going to see in just a second, working in terms of y here is actually going to be much easier than working in terms of x. So let's work on that here. These two integrals were for part A, but now let's work on part B. We want to calculate that same area, but now with an integral or possibly integrals in terms of y. And when you want to calculate the area between two curves, or again, in this case, we're working with lines, but regardless, when you want to calculate the area between two curves in terms of y, instead of looking from the top down, you look from right to left. What is the rightmost function and what is the leftmost function? And in this case, the rightmost function of the region is y equals x. This line bounds that region entirely between the two values of y for which the region is located. Right, the region is between y equals 0 and y equals 4, and y equals x is the rightmost function for that entire region. And then the leftmost function for that region is y equals 8x. That will bound the region entirely on the left. Okay, nothing changes here. No matter where you draw a line from right to left through that region, you will always hit the same two lines. So there's no need to split up the region here. We don't have to set up two integrals like we did in terms of x. We can use one integral because there's only one rightmost function and one leftmost function for the entire region. Okay, so let's set up our integral here. We are going to be integrating in terms of y, and as I mentioned earlier, we are going from y equals 0 to y equals 4. So we're integrating from 0 to 4. And then the rightmost function is y equals x, but remember, you're not going to use x this time because we're working in terms of y. So you want to write down y and then subtract the leftmost function, y equals 8x, but again, you want to be working in terms of y, not x. So do not write in 8x there. Instead, solve for x in this equation so that it's an equation of x in terms of y, which you can do pretty quickly. Just divide both sides of the equation by 8, and you will find that x is equal to y divided by 8, or 1/8 times y. So that's what we are going to subtract in the integral. The leftmost function is 1/8 times y. And so close that parenthesis and then write dy, and you're good to go. This integral right here represents the area of this region, but when we're working in terms of y. And if we set it up correctly, which we did, it will give us the same exact answer for the area that our integrals in terms of x did. Okay, so we should still get 7. But let's make sure, let's evaluate this integral. First thing I'm going to do here is combine these two terms. They are like terms. So this is equal to the integral from 0 to 4 of 7/8 y dy. And then integrating y, you want to add 1 to the exponent and then divide by that new exponent. So that will give you 7/8 times 1/2 y squared, evaluated from 0 to 4. And then you want to evaluate this expression at 4 and subtract the evaluation at 0. Okay, so I'll do that right here. That will be equal to 7/8 times 1/2 times y squared, where y is 4. So you'll have 4 squared, and then you'll be subtracting 0, right? Because if you plug 0 into this expression, you will just get 0. So simplifying this then, 4 squared is 16. 16 times 1/2 is 8. So we get 7/8 times 8, and those 8s will cancel out, giving you the same exact answer of 7. 7 is the area of this region, no matter if you work in terms of x or in terms of y for your integrals. Okay, let's move on to the next problem. For problem 8, we want to find the first, second, third, fourth, and nth Taylor polynomials centered at c equals the natural log of 3. And our given function is f of x is equal to e to the power of 2x. Okay, so remember, the form of a Taylor polynomial looks like this. A Taylor polynomial p for a particular value of n of x is equal to the sum from k equals 0 to that value of n of the following expression. We have the k derivative of f evaluated at c times x minus c to the power of k divided by k factorial. Okay, so if you want the first Taylor polynomial for a function, you want to set up this polynomial where n is equal to 1. So in that case, you would have a term for k equals 0 and then a term for k equals 1, giving you two terms that are added together from this series. All right, then for the second Taylor polynomial, you would set this up where n is equal to 2, so there would be an additional term. Then for the third Taylor polynomial, you would work with n equals 3, so there would be an additional term. And then for the fourth Taylor polynomial, that's where n is equal to 4, and so then there would be another term on top of that. Okay, but in each case, the value of n tells you what derivative you need in order to set up that Taylor polynomial. What I mean by that is for the first Taylor polynomial, you will need at least the first derivative of the function. To find the second Taylor polynomial, you'll at least need the second derivative. And then for the third and fourth Taylor polynomials, you'll need the third and fourth derivatives. That's just based on this formula. Okay, so if we want to find the first, second, third, and fourth Taylor polynomials, we'll come back to the nth, but for these first four, we know that we're going to need up to the fourth derivative of this function. So let's start with that. Let's find the first four derivatives of f of x, and then from there, we will build those Taylor polynomials. So starting with the first derivative, f prime of x, we want to take the derivative of e to the power of 2x, and remember that the derivative of an exponential function with a base of e is just equal to itself. But because that power here is not just x, it's 2x, we do also want to multiply by the derivative of that exponent. Okay, so we'll rewrite e to the power of 2x, but then multiply by the derivative of 2x, which is 2. Okay, so we have 2e to the power of 2x for the first derivative. Now for the second derivative, f double prime of x, we'll take the derivative of the first derivative, which is really going to be the same derivative, it's just that we're going to be multiplying by another 2 when we take the derivative of that exponential part. All right, the derivative will just be this function again, but then multiplied by another 2. So we get 4 times e to the power of 2x. Then moving on to the third derivative, f triple prime of x. We want to take the derivative again, so we'll differentiate the second derivative. It's just going to be the same function again, but multiplied by another 2, and 4 times 2 is 8, so we get 8 times e to the power of 2x. And then finally, the fourth derivative, which is denoted like this, we have f and then 4 in parentheses of x. That will be equal to the derivative of the third derivative. And so we'll just get the same function again, but multiplied by another 2. And 8 times 2 is 16, so we get 16e to the power of 2x. Okay, so now we have the first 4 derivatives of our function that will be very helpful for setting up these different Taylor polynomials. But also notice that when we go to set up those terms, that the derivative is always going to be evaluated at c, the value that we're centered at. So now what we should do is evaluate each of these derivatives and the original function at that value of c. That way we just have those values ready to go. Okay, so let's start by evaluating f at the natural log of 3. That is our value of c. So doing that, we get e to the power of 2 times x, which is now the natural log of 3. All right, now we can simplify this nicely because e and the natural log function are inverse functions. They cancel each other out. But before you can make use of that, you need to get rid of that coefficient of 2 from the natural log function. So an easy way around that is to just rewrite the expression like this. You can rewrite it as e to the power of the natural log of 3, and then take that to the power of 2. And that's the same thing, because when you have a value raised to an exponent raised to an exponent, the way you simplify that is by multiplying those exponents, right? So this would simplify to 2 times the natural log of 3 as the exponent of e. But writing it in this way allows us to make a nice simplification. E and the natural log are inverse functions, so they cancel each other out, just leaving you with that 3. Okay, so what this becomes is 3 to the power of 2, or 3 squared, which is equal to 9. So what we found here is that e to the power of 2x evaluated at the natural log of 3 is equal to 9. We can use that to our advantage to then evaluate these derivatives, because all of them include e to the power of 2x. So if we're going to evaluate those derivatives at x equals the natural log of 3, we can very quickly calculate those evaluations by just multiplying 9 by those constants, because we know e to the power of 2x at that value is 9. Okay, so we get f prime of the natural log of 3 is equal to 2 times 9, which is 18. Then we get f double prime of the natural log of 3 is equal to 4 times 9, which is 36. Then f triple prime of the natural log of 3 is equal to 8 times 9, which is 72. And then the fourth derivative evaluated at the natural log of 3 is equal to 16 times 9, which is 144. All right, and now we have everything we need. We are now ready to set up the first, second, third, and fourth Taylor polynomials, specifically ones that are centered at c equals the natural log of 3. So let's work on that here. Starting with the first Taylor polynomial, which would be p1 of x, that will be equal to the sum of two terms based on this expression. We'll first use k equals 0, and then k equals 1. So for k equals 0, you would have the 0 derivative, which is just the original function, so f of c, multiplied by x minus c to the power of 0 divided by 0 factorial. Okay, so you have f of c times x minus c to the power of 0 divided by 0 factorial. Now 0 factorial is equal to 1, and x minus c to the power of 0 is also equal to 1. Anything raised to the power of 0 will be 1. So that first term will just be equal to f of c, and f of c is our function evaluated at the natural log of 3, which is 9. So that first term will just be 9. Then we'll add that to the term where k is equal to 1. So we'll have the first derivative at c, right, f prime of c times x minus c to the first power divided by 1 factorial. And 1 factorial is just 1. So these two expressions are being divided by 1. So we really don't need to write that. X minus c to the power of 1 will just be itself. We just need to replace c with the natural log of 3. And then f prime of c, or f prime of the natural log of 3, is equal to 18. So what we get here is 18 times x minus the natural log of 3. That right there is the first Taylor polynomial for this problem. Now let's find the second Taylor polynomial, which would be p2 of x. It will share the first two terms of the first Taylor polynomial, but then add on a third term where k is equal to 2. Okay, so we have 9 plus 18 times x minus the natural log of 3. And then we will add on the second derivative evaluated at c times x minus c squared divided by 2 factorial. Now 2 factorial is just 2, so I'm going to erase that factorial, and we'll just have 2. And then f double prime of c is f double prime of the natural log of 3, which is 36. So I will erase this, and we'll have 36 times x minus c squared. So that c will be the natural log of 3, and 36 divided by 2 is 18. So what we get here is 18 times x minus the natural log of 3 squared. That's all we needed to add on. That will complete the second Taylor polynomial for this problem. Now let's find the third Taylor polynomial. That would be p3 of x. It will share the same first 3 terms of the second Taylor polynomial. So I've just added them in here again. The only thing that's going to be new is a fourth term involving the third derivative, right? We'll have f triple prime of c times x minus c cubed divided by 3 factorial. Now 3 factorial is 1 times 2 times 3, which is 6. So the denominator here is really just 6. And then f triple prime of c is the third derivative evaluated at the natural log of 3, which is 72. So replace that with 72. And that is multiplied by x minus c cubed, where c is the natural log of 3, and then 72 divided by 6 is 12. So altogether, simplifying that, the new term is 12 times x minus the natural log of 3 cubed. And that completes the third Taylor polynomial. Now let's move on to the fourth Taylor polynomial, which would be p4 of x. The fourth Taylor polynomial will include all of the terms from the third Taylor polynomial plus an additional term. So this is what we have so far, but then we want to add on one more term where k is equal to 4. So we have the fourth derivative evaluated at c times x minus c to the power of 4 divided by 4 factorial. Now 4 factorial is 1 times 2 times 3 times 4, which is 24. So that denominator is 24. So I'll write that in there. And then the fourth derivative evaluated at c we found was 144. So replacing that with 144, we get this. And then x minus c to the power of 4, you want to replace that c with the natural log of 3, and then 144 divided by 24 is 6. Okay, so altogether, that term simplifies to 6 times x minus the natural log of 3 to the power of 4. And that right there is the fourth Taylor polynomial for this problem, which means there's only one more Taylor polynomial left to find, and that is the nth Taylor polynomial. And this one's a little bit trickier because we have to write everything in terms of n, or really we're just going to use this formula here, where the sum is in terms of n for that nth polynomial, but we are working in terms of k for the actual expression in that sum. But really the only things we need to change here is replace this c with what it's equal to, which is the natural log of 3, and then find an expression for the nth derivative evaluated at c, or really it's the k derivative. But if we're going up to the value of n, just think of it as the nth derivative. And so what would that be? How would we represent the nth derivative evaluated at c? Well, we have to go back to our derivatives evaluated at c and look for some kind of pattern. And so if we're just looking at the final results, it can be kind of tricky to figure out what the pattern is or how we'd represent it with an expression. But if you look at how they were calculated, you had 2 times 9, then 4 times 9, then 8 times 9, then 16 times 9. Each time it increased by a factor of 2. Okay, you had 2 times 9, then 2 squared, which is 4 times 9, then 2 cubed times 9, and then 2 to the power of 4 times 9. Okay, so what's going on here, I'll write it right here. The pattern is that the nth derivative evaluated at the natural log of 3 is equal to 2 to the power of n times 9. Okay, notice that the first derivative had 2 to the first power. The second derivative had 2 to the second power, or 2 squared, which is 4. The third derivative had 2 to the power of 3, which is 8. And the fourth derivative had 2 to the power of 4, which is 16. Okay, so that's the pattern. It holds true. We can replace the nth derivative, or really it's the k derivative, with this expression. Just make sure you write it in terms of k. So what we get here for the nth Taylor polynomial is p sub n of x is equal to the sum from k equals 0 to n of 9 times 2 to the power of k. I'm just putting the constant out front. It doesn't really matter, but that's how I prefer to write it. But this is the same expression that we had here. That is our k derivative evaluated at the natural log of 3. And that will be multiplied by x minus c, which is the natural log of 3 to the power of k. And then that is divided by k factorial. That right there would be the nth Taylor polynomial for this problem. And so with that, we have now found everything we needed to find. We found the first, second, third, fourth, and nth Taylor polynomials for this function centered at c equals the natural log of 3. Next up, for problem 9, we want to evaluate the integral, and we're given the integral of 2x squared plus 5x minus 8 divided by the quantity x minus 2 multiplied by the quantity x squared plus 1. Okay, so what we've been given here is an integral involving a rational expression where we have a quadratic expression in the numerator and then these two factors in the denominator. And in order to integrate an expression like this, we will need to make use of the method of partial fraction decomposition. Okay, because in its current state, this is not something that we know how to integrate, right? Perhaps you could try to expand the denominator, but it's going to be very unlikely that that will be an expression that you could use u substitution on, where you could set that equal to u and its derivative is in the numerator. That's going to be very unlikely. Usually when you see an integral like this, you are expected to use partial fractions. So let's set that up here. We want to break down the fraction 2x squared plus 5x minus 8 divided by x minus 2 times x squared plus 1. And it's going to be broken down into two different fractions. We're going to have a fraction for each of these factors in the denominator. We're going to have one for x minus 2 and another one for x squared plus 1, right? One fraction will have a denominator of x minus 2, and then you'll add that to another fraction whose denominator will be x squared plus 1. The idea here is that this fraction is the result of these two fractions added together when you get a common denominator between them. Okay, but now what goes in the numerator? Well, when you have a linear factor, like we do here, meaning x is to the first power, and specifically this is a distinct linear factor, because the linear factor is not being squared, it would be raised to a power of 1. But anyway, when that denominator is a linear factor, the numerator will just be a constant. So I'll represent that with a. Then for this fraction, the factor is a distinct quadratic factor, right? X is being squared, but the whole factor itself is to the power of 1. Right, we just have x squared plus 1 as a quantity. It's not being squared or anything like that. It is a distinct quadratic factor. And when you have a quadratic factor, the numerator needs to be a linear expression. So I'll represent that with a constant of b times x to the first power plus a constant term c. Okay, so remember, for partial fraction decomposition, whatever type of factor you have in the denominator, the numerator will always be 1 degree less. So if you have a factor with x to the first power, the numerator will be a constant, where x is essentially to the power of 0. And when you have a quadratic factor, where x is to the power of 2, the numerator will be a linear factor, where x is to the power of 1. It is 1 degree less. Alright, but that's the setup. Now what we need to do is figure out what a, b, and c are equal to, so that we can rewrite this integral by replacing this fraction with its partial fraction decomposition. And so here's how we're going to do that. Remember that you would want to get a common denominator between these two fractions so that you can combine them together and have the same denominator as this fraction over here. And then this numerator would be equal to the combined numerators of these two fractions. All right, so to shortcut that, here's what you can do. Take the expression from the numerator of the original fraction, so 2x squared plus 5x minus 8, and set that equal to these numerators, but multiplied by the factors, or in this case, just the factor that is not in their denominator, right? So for this fraction, a already has a denominator of x minus 2, so if you were trying to get a common denominator, you would have to multiply this fraction by a form of 1 of x squared plus 1. So just set the numerator of this fraction equal to a times that factor of x squared plus 1, and then add that to the numerator of this fraction multiplied by the factor that it doesn't have in its denominator, which would be x minus 2. All right, so we have bx plus c times x minus 2. Okay, you would multiply this fraction by a form of 1 of that factor divided by itself in order for these two fractions to have a common denominator so that you could add their numerators and compare it to this numerator right here. And so doing that, this is what you would get. And now we can focus solving on A, B, and C. And the first thing I'm always looking for when solving for those constants is there any value that I could set x equal to in this equation such that it will eliminate some of the constants so that I can solve for another one? Here's what I mean by that. Notice this quantity right here of x minus 2. If we let x be equal to 2 in this equation, then this whole term would be 0. Because you'd have 2 minus 2, which is 0, and 0 times this factor involving both b and c, well, that whole thing would be 0 because anything times 0 is 0. So you would just have an equation involving a where you could solve for a. Okay, it doesn't matter what value of x you plug into this equation, this side of the equation should be equal to this side. So if you just choose a convenient value of x such that part of it becomes 0 so that you can just solve for another constant, then you should do that. Okay, so if I let x equal 2, then we'll have 2 times 2 squared plus 5 times 2 minus 8 is equal to a times 2 squared plus 1 plus b times 2 plus c multiplied by 2 minus 2. Again, that's just equal to 0. So this whole thing becomes 0. And really, we're just working with a times 2 squared plus 1 and this side of the equation. All right, so 2 times 2 is 4, times 2 is 8. So we have 8 plus 5 times 2, which is 10, minus 8, and that's equal to a times 2 squared plus 1, which is 4 plus 1, and that's 5. So we have 5a on that side, and then over here, positive 8 and negative 8 cancel out, so you can cross those out, they become 0, which means we have 10 is equal to 5a, and dividing both sides by 5 will give you that a is equal to 2. Okay, so now we have one of our constants. We were able to find it by letting x equal 2. And so back to our original equation, are there any other convenient values of x that we could plug in so that we could solve for b or c? And the answer is kind of. We could let x be equal to 0. And so then right here, you'd have b times 0, which is 0. So b would be gone, just leaving you with c and a in the equation. And since we already know what a is, that's okay. We should be able to solve for c if we do that. So that's what I'll do here. Let's let x be equal to 0. If x is 0, on this side of the equation, this term and this term will just become 0. So you'll just have negative 8 is equal to these terms. All right, so we've got negative 8 is equal to a times 0 squared plus 1 plus b times x. So that's going to be 0, but then plus c, and then 0 minus 2. Now 0 squared is 0, plus 1 is 1. So we have 1 times a, but a is equal to 2. So I will replace that with 2. We have negative 8 is equal to 2, plus b times 0 is 0. So you just have 0 plus c, which is c. And c is being multiplied by 0 minus 2, which is negative 2. Okay, and then to solve for c, subtract 2 from both sides, giving you negative 10 is equal to negative 2 times c, and then dividing both sides by negative 2 will give you positive 5, because negative 10 divided by negative 2 is 5. So what we find here is that c is equal to positive 5, and now we have solved for 2 of those constants, right? We now know a and c. There's only one left to find here, and that is b. And so to find b, what we can do is just pick any value of x to plug into this equation and then solve for b. Because now that we know what a and c are, we can just put those values into the equation as well, and b will be the only unknown value. Okay, so let's do that here. As I said, you can pick any value of x you like, but I'm going to pick one that is nice to work with that we haven't already used, because we can't use 2 or 0, as that would remove b from the equation. We want to pick a value of x such that b is not gone. So let's just pick a nice value like 1. If you let x be equal to 1, here's what you'll get. You'll have 2 times 1 squared, which is just 2, plus 5 times 1, which is just 5. So on that side of the equation, we have 2 plus 5 minus 8, and that will be equal to a times 1 squared plus 1. So 1 plus 1 is 2. You'll have 2 times a, where a is 2, and 2 times 2 is 4. So we have 4 plus b times x, where x is 1. So just b plus c, where c is 5, right? That's what we just found right here. And then that is multiplied by x minus 2, which will be 1 minus 2. All right, now simplifying, 2 plus 5 is 7, minus 8 is negative 1. So we have negative 1 is equal to 4 plus b plus 5 times negative 1, right? 1 minus 2 is negative 1. So distribute negative 1 through this quantity, and you'll get negative b minus 5. So I'll write that down here. And then 4 and negative 5 combine to be negative 1. So we have negative 1 is equal to negative 1 minus b. And then if you add 1 to both sides of the equation, what you find is that 0 is equal to negative b, and then you can multiply both sides by negative 1. It doesn't matter. What we find here is that b is equal to 0. And now we have the values for all 3 of the constants. We know that a is 2, b is 0, and c is 5. So we can replace a, b, and c in our partial fractions here, and we will be able to use those fractions to rewrite this integral into a form that we can actually integrate. Okay, so let's replace them here. We know that a is equal to 2. We know that b is 0, so 0 times x is 0, just leaving you with c, which is 5. So we'll have 5. Okay, so this fraction that we started with in our integral can be rewritten as 2 divided by x minus 2 plus 5 divided by x squared plus 1. So let's do that here. We can now finally go back to working on the integral, and this will be equal to the integral of 2 divided by x minus 2 plus 5 divided by x squared plus 1. And then don't forget about dx. And then what we want to do is split up that integral into 2 integrals. I suppose if you're really good at integrating, you don't need to do that, but I like to do it so that I can focus on each fraction individually. So I'm going to split it up. We'll have the integral of 2 divided by x minus 2 dx plus the integral of 5 divided by x squared plus 1 dx. Okay, now what I'm going to do here is pull out those constants. I'll pull 2 out to the front and 5 out to the front for each of those integrals. So in each case, we'll just have 1 in that numerator, and then 2 out front of this one, and 5 in front of this one. All right, and now we're almost done because both of these expressions can be integrated pretty quickly. For this first one here, you can just use the log rule for integration. Technically, you do need to use u substitution because you would want to set that denominator equal to u, but its derivative is just 1, right? The derivative of x minus 2 is 1. So whenever that's the case for an integral where you would use u substitution, really at this point in calculus, you can just skip it and go straight to the final answer because you know that you'd be integrating 1 divided by u, which results in the natural log of the absolute value of u, and then you'd replace u with what you set it equal to. Okay, so this just becomes 2 times the natural log of the absolute value of x minus 2. That is the result for that integral. And then you'll add that to 5 times the integral of 1 divided by x squared plus 1, which looks complicated at first, but this actually lines up perfectly with an integration rule that you learn in Calculus 1. The integral of 1 divided by x squared plus 1 is just the inverse tangent function. It's equal to arctangent of x. Okay, so we get 5 times arctangent of x, and then don't forget to add your constant plus c. And that's it. That right there is the final answer for the solution to this integral. Okay, and so as we would expect with these partial fraction decomposition integrals, the hardest part is usually the algebra involved with the partial fractions. Once you actually get those partial fractions, the calculus part is usually not too bad. But that's it for this problem. Let's move on to the next one. For problem 10, we have 7 1/2 foot-pounds of work is required to compress a spring 2 inches from its natural length. Find the work required to compress the spring an additional 1/2 inch. Okay, so what we've been given here is a work problem. We want to find the work required to compress a spring a particular distance. And so not only is this a work problem, but it is a work problem involving springs. And so remember, the general formula that we use for calculating work of a variable force, as we do in Calculus 2, is that the work is equal to the integral from a to b of the force function, capital F of x, dx. All right, and in the case of a spring work problem, that force function, capital F of x, is equal to the spring constant k times x. All right, and in this problem, we are not told what that spring constant is, right? Nothing in this problem tells us anything about the spring constant. So that's something that we want to keep in mind here. But now let's go back to the problem and figure out what kind of calculations we can set up. First of all, we know that 7½ foot-pounds of work, that is an amount of work W, that amount is required to compress a spring 2 inches from its natural length. Okay, so this first sentence is describing one scenario, and then the second sentence is a slightly different scenario. It tells us to find the work required to compress the spring an additional 1/2 inch. But before we can figure that out, we do need to know what the spring constant is, right? In order to calculate work done in compressing a spring, you need that spring constant. And so it's most likely going to be the case that we can figure out what it is from the information that we are given in the first sentence. From this information, we can set up a work integral that will allow us to solve for that spring constant, right? If 7½ foot-pounds of work is required to compress a spring 2 inches from its natural length, we can let W be equal to 7.5. So we'll have 7.5 equal to the integral of the force function, which in this case will be the spring constant k times x. So I'll write that in here. We have k times x dx. But then what about the bounds of integration? Well, we always think of the natural length of a spring as being where x is equal to 0. So if you're compressing a spring 2 inches from its natural length, you'll be integrating from x equals 0 to x equals 2 inches. And you have to be careful here. Don't just write in 2, because our given value of work for this scenario, 7.5, is measured in foot-pounds. Okay, so the units have to match up. You can't use work in terms of feet and then integrate in terms of inches. You want the bounds of integration to also be measured in feet. Okay, so we have to do a little conversion here. We have to figure out what 2 inches would be in terms of feet. And remember that there are 12 inches in 1 foot. So what that tells us is that 2 inches is 2/12 of a foot. Okay, so simplifying that, what we get is 1/6 of a foot. That is 2 inches in terms of feet. So that's going to be our upper bound for this integral. We will integrate from 0 to 1/6. Okay, and now we're good to go. We can integrate this expression, even though we don't know what k is. It's just a constant, right? It's just the spring constant for this scenario. So we can still integrate this expression. And then once we do integrate it, we should be able to solve for x, since we know the amount of work for this scenario. All right, so let's integrate x, add 1 to the exponent, and divide by that new exponent. Doing that, you'll get 7.5 is equal to that spring constant k times x squared divided by 2, evaluated from 0 to 1/6. Okay, so continuing my work over here, 7.5 will be equal to the spring constant multiplied by this expression evaluated at 1/6 minus evaluating it at 0, which if you plug 0 into this expression will output 0. So we don't need to worry about that, but it's always good to check. Really, we just need to plug in 1/6 and we're good to go. So we'll have 1/6 squared divided by 2. And I'm going to pull that 1/2 out. Really, this will be 7.5 is equal to k divided by 2 times 1/6 squared. 1 squared is 1, so really you just have 1 divided by 6 squared, which is 36. And 36 times 2 is 72. So we have 7.5 is equal to k divided by 72. And so then multiplying both sides by 72, we can solve for k. 7.5 times 72 gives you 540, so we have just found that the spring constant k is equal to 540. That is what it would have to be in order for that first statement to be true. If 7.5 foot-pounds of work is required to compress a spring 2 inches or 1/6 of a foot from its natural length, then the spring constant has to be 540, specifically 540 pounds per foot. Okay, but now that we have that, we can use it to actually answer the problem because we want to find the work required to compress the spring an additional 1/2 inch. Okay, so let's set up that integral. We're going to use the same work integral that we used here, but now we don't know what the work is. That's what we need to find. So W will be equal to the integral, and we'll come back to those bounds of integration. Let's just set up the rest of it. We'll have the spring constant K, which is 540, times X. So I'll write that in here, 540X times dx. But now what about the bounds of integration? Well, if we're compressing the spring an additional 1/2 inch, we're no longer starting at the natural length of 0. We're going to be starting where we ended last time, which was 1/6 of a foot or 2 inches. So that's going to be our new lower bound. But then the upper bound will be that starting length plus an additional 1/2 inch. Okay, and be careful, that's not 1/2 of a foot, that's not 6 inches, it's 1/2 of an inch. All right, in other words, that is 0.5 inches. So what would that be equal to in terms of feet? Well, again, there are 12 inches in a foot, so you would have 0.5 divided by 12. That would represent 1/2 of an inch in terms of feet, but we can make that look a little bit nicer. That 0.5 you could represent as a fraction, which would be 1/2. So you have 1/2 divided by 12, which is the same as 1/2 times 1/12, which simplifies to 1/24. Okay, so 1/24 of a foot is the additional length that the spring is being compressed. Okay, so again, be careful. That is not the new upper bound. We need to add that to the existing lower bound. Because the spring is already compressed 1/6 of a foot, we need to compress it an additional 1/24. Okay, just as a demonstration, if this is our spring, if you think of this spring as being at its natural length, and we compress it this amount right here, which is 1/6 of a foot, and then we compress it an additional 1/24 of a foot, the total compression will be 1/6 plus 1/24. The spring has this natural length, but we're compressing it or pushing it in this total amount. But we're starting at this distance of 1/6, but we're moving an additional 1/24. Okay, so we need to add those fractions together. 1/6 plus 1/24 will be equal to what? Well, 1/6 in terms of 24ths would be 4/24. So 4/24 plus 1/24 is 5/24. So that would be our new upper bound. Okay, so we're going to integrate from 1/6 of a foot to 5/24 of a foot. And that's it. The setup is done. We now just need to evaluate this definite integral. So let's do that. To integrate x, you need to add 1 to the exponent and divide by that new exponent. So you'll be dividing 540 by 2, which is 270. So this is going to be equal to 270x squared, evaluated from 1/6 to 5/24. And so plugging in 5/24 and subtracting plugging in 1/6, this will be equal to 270 times 5/24 squared minus 1/6 squared. All right, now if you simplify this, 5/24 squared is 25/576, and 1/6 squared is 1/36. And so if you take this fraction, subtract that fraction, you will get 1/64. So this is equal to 270 times 1 divided by 64, which as a fraction becomes 135 divided by 32. Okay, but since the work earlier was given as 7 1/2 foot-pounds, it wasn't given as a fraction, let's write out the decimal value for this fraction as well. What we find here is that the work is equal to 4.21875 foot-pounds. And that is the exact value, okay? It's pretty many decimals, but that is it. It does end there. That is the amount of work required to compress the spring an additional 1/2 inch. So that is what you should get if you put this calculation into a calculator, or if you do it by hand and you get this fraction as a decimal is this value. But that's it for this problem. Let's move on to the next one. Next up, for problem 11, we want to determine if the series converges or diverges. And we're given the sum from n equals 1 to infinity of 2n squared minus n plus 1 divided by 5n squared plus 3n plus 2. Okay, so to determine if this series converges or diverges, we have a lot of different series tests to choose from, and so if you're not exactly sure what to do or what test to use, a good place to start is to always try the divergence test. take the limit as n approaches infinity of the nth term from your series and see if that limit is equal to 0 or not. If it's equal to 0, then the divergence test isn't helpful, it's inconclusive, so you will have to use another test. But if that limit's not equal to 0, if it's equal to some other value, whether it's finite or infinity, then you're done. You've shown from the divergence test that the series diverges. So it's always good to check that, because it is a quick test, assuming that the limit is something that you can actually evaluate, which in this case it will be. So let's set it up. Let's take the limit as n approaches infinity of 2n squared minus n plus 1 divided by 5n squared plus 3n plus 2. Okay, now if you're very familiar with evaluating limits at infinity, this is a pretty quick limit. Whenever you have a limit at infinity of a rational expression or a fraction involving a polynomial divided by another polynomial, there are some nice shortcuts that you can take advantage of. Specifically, you want to look at the highest power of the variable in the numerator and denominator. If the highest power in the numerator is bigger than the highest power in the denominator, then the limit will be equal to infinity. But if the highest power in the denominator is bigger than the highest power in the numerator, then the limit will be equal to 0. Or the third option, if the highest power in the numerator and denominator is the same, then the limit will be equal to the ratio of the coefficients of those terms. And that is what's going on here, right? The highest power of n in the numerator is 2. We have this n squared. And the highest power of n in the denominator is also 2. We have this n squared. So since the highest powers of n are the same in the numerator and denominator, this limit will just be equal to the ratio of their coefficients. In other words, 2 divided by 5. 2 is the coefficient of this n squared, and 5 is the coefficient of this n squared. So really quickly, we can just say that this limit is equal to 2/5, which is not equal to 0, which from the divergence test means that this series diverges. And that's it. We would be done with this problem and can move on to the next one. Okay, so I highly recommend that you learn that shortcut for quickly evaluating limits at infinity. It's something that you should have learned in Calculus 1, but sometimes we forget it later on, and that's okay. That's why I wanted to remind you of it here. But if for some reason you can't remember those rules or don't want to use them, you can go the algebra route, which is to multiply this expression or multiply the limit by a form of 1 divided by the highest power. Okay, so we have the limit as n approaches infinity of 2n squared minus n plus 1 divided by 5n squared plus 3n plus 2. Looking at the numerator and denominator, the highest power of n that we see is n squared, so we want to multiply by a form of 1 divided by that highest power. Okay, so 1 divided by n squared divided by itself. And so if you simplify that, you will get the limit as n approaches infinity of 2 minus 1 divided by n plus 1 divided by n squared divided by 5 plus 3 divided by n plus 2 divided by n squared. Okay, so 1 divided by n squared multiplied through the numerator here cancels out with this n squared, just giving you 2. Then negative n times that just leaves you with negative 1 divided by n. One of those n's in the denominator cancels out with that n, and then that value times 1 just gives you that value again. Then in the denominator, 1 divided by n squared times 5n squared, those n squareds cancel out, just giving you 5. And then multiplying it by 3n, one of those n's cancels out, so you have 3 divided by n, and then 2 times 1 divided by n squared gives you 2 divided by n squared. And the reason why this is helpful is because now, if we take the limit as n approaches infinity of the numerator and denominator, the limit of 2 is just itself, it's a constant, and then this negative 1 divided by n, as n approaches infinity, you would have 1 divided by infinity, so a fixed number divided by infinity for a limit that approaches 0. Same thing would happen for 1 divided by n squared. That denominator would just be approaching infinity. And in the denominator, the limit of 5 as n approaches infinity will be 5. But then 3 divided by n is approaching infinity. So you have a fixed number divided by an infinite value. That will approach 0 for the limit. And then 2 divided by n squared, same thing. That denominator will approach infinity. And you have a fixed number divided by it. So that will approach 0 as well. So what you get here for the limit is 2 minus 0 plus 0 divided by 5 plus 0 plus 0, which equals 2/5. So the same answer that we got before, but it just took a little bit longer to get there. and involved more work. That's why I recommend that you learn those rules for evaluating limits at infinity for an expression like this, because it's quicker and will save you time that you can spend on other problems on your exam. Okay, but the result is the same. When you take the limit as n approaches infinity of that nth term from the series, you don't get 0, you get some other value, in this case 2/5. So from the divergence test, we know that this series diverges. Okay, so if you want to make a note of that, you can, so that whoever's looking at your work knows what test you used. But at this point, we're done. We used the divergence test, we didn't get 0, so we know the series diverges, which is a nice result. So always be sure to check the divergence test if you're not sure what to do first for a series. It might save you a ton of time if you immediately find that the series diverges. It may be the case that sometimes that limit is too complicated to solve, so you wouldn't want to use the divergence test in that case. There's most likely another test that is going to work way better. So if the limit gets too complicated or something and you can't solve it, just move on to a different test. That's my general advice there. Okay, but that's it for this problem. Let's move on to the next one. For problem 12, we want to evaluate the integral, and we've been given the integral of x cubed divided by the quantity 3 plus x squared to the power of 5/2. And we're not told what method of integration to use here. We have to figure that out ourselves. So looking at this expression that we have to integrate, what integration methods might make sense to use? Because just by looking at this expression, it doesn't really line up with any of our basic integration rules, right? We can't use anything like the power rule of integration here. And this also really isn't in a form that corresponds to something that integrates into an inverse trig function, which is something that you want to be on the lookout for when you have a rational expression or a fraction. But that's not going to apply here. And so thinking about some of our other more advanced techniques for integration, the first thing I always try to see if I can use is u substitution. And so looking at this expression, there's really only two choices for what we could set equal to u. You could set the numerator equal to u, but its derivative is not within the integral. Right, if you take the derivative of x cubed, you'll get an expression involving x squared, which can't be found within the integral. Yes, we do have this x squared in the denominator, but it is in the denominator, so technically that power is negative, and it's also being raised to a power of 5/2, not to mention that you're adding it to a constant within a quantity being raised to that power. Okay, so setting the numerator equal to u is not going to work, and so the other option would be to set this quantity of 3 plus x squared equal to u, but that also won't work because the derivative of that is not within the integral either. The derivative of 3 plus x squared would be a function involving x to the first power. And what we do have in the integral is x to the power of 3. Okay, so that doesn't line up. U substitution isn't really going to work here. So let's think about the other integration methods that we have at our disposal. We know that integration by parts is something that we can do, but that's not really going to be helpful for this integral because when we use integration by parts, we're typically looking for a product of two different types of functions. Whether that's an algebraic function times a trig function or a trig function times an exponential function, right? Those types of products of functions is where integration by parts is useful. That's not really what we have here. We have a rational expression with a radical denominator because of that 5/2 power. Whenever you have a fractional power, that is a radical expression or something dealing with a root. And so integration by parts doesn't make sense to use here. And so then moving on from that, there are no trig functions in this expression, so our methods for solving trigonometric integrals do not apply here. But something that could work is trig substitution. That would be the next thing that comes to mind here. Because whenever you have a rational expression involving a radical or some quantity raised to a power in the denominator, trig substitution is a viable option. And so taking a closer look at this expression, particularly the denominator, we have something that can be compared to a particular form that we associate with a specific trig substitution. In this case, we have a constant plus a variable squared that is being raised to a power. We could compare that to this form of the square root of a constant a squared plus a variable expression u squared, which corresponds to a trig substitution of setting u equal to a times tangent theta. Right, remember for trig substitution, there are different forms that we are on the lookout for that correspond to specific substitutions. Usually we're looking for a square root in those forms, but it doesn't really matter. You can still apply it to quantities being raised to any fractional power. Trig substitution will still be helpful here. Okay, we can think of a squared as being 3 and u squared as being x squared, right? So if a squared is equal to 3, then what that implies is that a is equal to the square root of 3, because to solve for a, you would need to take the square root of both sides. And from that, we just want to use the positive result of the square root of 3. And so then in the same way, u squared being equal to x squared implies that u is equal to x, right? So u squared equals x squared, which implies u equals x. And again, we're just working with positive x and the positive square root of 3. So together, using these values for a and u, we now know that the trig substitution that we can make for this integral is to let x be equal to the square root of 3 times tangent theta, right? Because u is equal to x, so x is equal to a, which is the square root of 3 times tangent theta. This is the substitution that we are going to use. And so let's work with that. We are going to replace x in this integral with this expression, and so we will be rewriting the integral in terms of theta instead of x. So we also want to rewrite dx in terms of theta. To do that, we need to take the derivative of our substitution here. We want to take the derivative of x with respect to theta, and so that will be equal to the square root of 3 times the derivative of tangent theta, and the derivative of tangent is secant squared, so we have secant squared theta, and then we want to solve for dx, so multiply both sides by d theta, and you'll find that dx is equal to the square root of 3 times secant squared theta d theta. Okay, and so now we have everything we need. We can replace each of these x's with this expression, and we can replace dx with this expression, and our integral will be rewritten entirely in terms of theta, which hopefully should simplify to something that we can integrate. Okay, so let's rewrite the integral. This will be equal to the integral of x cubed, so replace x with the square root of 3 times tangent theta. So we will have that expression of the square root of 3 times tangent theta, but then cube it, and then that will be divided by the quantity 3 plus x squared. So now you're going to have this expression again, but now squared. And I'm going to do that squaring right away. If you square the square root of 3, you get 3, and squaring tangent gives you tangent squared. So we'll have 3 times tangent squared theta, and that quantity is to the 5/2 power. All right, now be careful here. This is where a lot of people will make mistakes in trig substitution problems. They'll forget to replace dx with what it's equal to in terms of theta. So don't just write d theta there. That would not be correct. You want to replace dx with this entire expression. So you want to multiply by the square root of 3 times secant squared theta d theta. All right, and so now our integral is in terms of theta. Now we just want to try to simplify it as much as possible. So let's work on that here. First thing I'll do is cube the numerator. So you want to cube the square root of 3 as well as tangent theta. Tangent theta cubed will be tangent cubed theta. And then the square root of 3, if you're cubing that, you're just multiplying it by itself 3 times. So you'd have the square root of 3 times the square root of 3 times the square root of 3. The square root of 3 times itself is just 3, so you'll have 3 times the square root of 3. Okay, so let's rewrite the integral here. This will now be equal to 3 square roots of 3 times tangent cubed theta. But then notice that we have this square root of 3 times secant squared theta that we can multiply into the numerator. So I'll do that here. We'll multiply by the square root of 3 times secant squared theta, and then that will be divided by this denominator. Now the reason why trig substitution is helpful is because usually that denominator can be simplified using a trigonometric identity. And so we will do that, but first we want to pull out that common factor of 3 from these two terms. And then we will see the trigonometric expression that can be replaced using a trig identity, specifically a Pythagorean identity. All right, so if we pull out that 3, we'll have 3 times 1 plus tangent squared theta, and that whole quantity is to the 5/2 power, and then don't forget about d theta. Now simplifying further, we've got 3 square roots of 3 times the square root of 3. The square root of 3 times itself is 3, so we have 3 times 3, which is 9. So I'll pull that out front of the integral. I'll write it like this. We have 9 times the integral of tangent cubed theta times secant squared theta, and then that is divided by this denominator, which we can now rewrite using a Pythagorean identity for tangent and secant, right? We know that 1 plus tangent squared theta is equal to secant squared theta. So we can replace this 1 plus tangent squared theta with secant squared theta. All right, so we'll have 3 times secant squared theta to the power of 5 halves, and then d theta. Okay, so now we're getting closer to an expression that we can integrate, but we do need to simplify further. Specifically, what we want to do next is now take both 3 and secant squared theta to the power of 5 halves, and so here's what that will look like. I'll continue my work over here. This will be equal to 9 times the integral of tangent cubed theta times secant squared theta, but then it will be divided by 3 times secant squared theta to the 5 halves power. So let's work on those one at a time, starting with 3 to the 5 halves power. If I do that work on the side here, 3 to the 5 halves power would be the same as 3 to the 1/2 power to the power of 5. Right? You can split up that exponent like this because if you were to simplify this expression, you would multiply the exponents and get back to 5 halves. Writing it like this just makes it a little bit easier to see what our calculation is, and we have 3 to the 1/2 power, which is the same as the square root of 3 to the power of 5. So we're multiplying the square root of 3 by itself 5 times. So we get the square root of 3 times 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 the square root of 3. These two square roots of 3 multiply together to become 3, as would these two. So we have 3 times 3, which is 9, times the square root of 3. That's what we'll have in the denominator. We'll have 9 times the square root of 3. At least that takes care of the constant, but don't forget about secant squared theta. If you take secant squared theta to the power of 5 halves. Just like with 3, this would be the same as taking the square root of secant theta and then raising it to the power of 5. Okay, so really this squared and this 1/2 cancel out in those powers, just leaving you with secant to the power of 5. Okay, so that's what I will write in the denominator. We have 9 square roots of 3 times secant to the power of 5 theta. And then don't forget about d theta. All right, and then continuing on, we now have a 9 in the numerator and denominator, so those are going to cancel out. And then we have secant squared theta in the numerator and secant to the power of 5 in the denominator. So this secant squared theta will cancel out with 2 of those secants in the denominator. We'll be left with secant cubed theta. All right, you just subtract 2 from that power of 5. And so rewriting the integral, I am going to pull out the constant of 1 divided by the square root of 3. So this will be equal to 1 divided by the square root of 3 times the integral of tangent cubed theta divided by secant cubed theta. And that's still multiplied by d theta. Okay, so now we're getting really close to an integral that we can integrate. We started out with a very complex expression, but now it's just tangent cubed theta divided by secant cubed theta. But we still can't integrate it in this form. This is not something that we have an integration rule for, and you can't use U substitution here, so we have to find a way to simplify this even further. And one of my general pieces of advice for trigonometric integrals that you're not sure how to solve is get everything in terms of sine and cosine and see if there is anything that you can cancel out. So if we do that here, we'll have 1 divided by the square root of 3 times the integral of tangent cubed theta. Remember that tangent is the same as sine divided by cosine. So tangent cubed would be sine cubed theta divided by cosine cubed theta. But then that would be multiplied by 1 divided by secant cubed theta. But remember that secant is defined as 1 divided by cosine. Or really, cosine is defined as 1 divided by secant. So 1 divided by secant cubed theta is the same as cosine cubed theta. So let's rewrite that as well. 1 divided by secant cubed theta is cosine cubed theta. And then we still have d theta on the end. Okay, but now everything in the integral is now expressed in terms of sine and cosine, which hopefully you can see why that is helpful, because now we have a cosine cubed theta in the numerator and a cosine cubed theta in the denominator that will cancel out. Cosine cubed theta divided by itself is 1. So you have 1 times sine cubed theta, which is just sine cubed theta. Okay, so here's the new integral that we get. We will have 1 divided by the square root of 3 times the integral of sine cubed theta d theta. And that is a much simpler integral than what we started with, and it is something that we can integrate. We now just have a very basic trigonometric integral where we have sine raised to a power, And so this is where we need to remember our rules for solving trigonometric integrals. If you have a trig function raised to an odd power, what you want to do is split that odd power up such that you have that trig function to the power of 2, where you can then replace it with a trigonometric identity, specifically one of the Pythagorean identities. Okay, so I'll split it up like this. We'll have 1 divided by the square root of 3 times the integral of sine theta times sine squared theta. Okay, we are allowed to do that. Sine times sine squared is sine cubed, but by writing it like this, we can then replace sine squared theta with a trigonometric identity that will then allow us to solve this integral using u substitution. Okay, so continuing my work up here, what we now have is 1 divided by the square root of 3 times the integral of sine theta times sine squared theta, but remember that sine squared theta is equal to 1 minus cosine squared theta. That is using the Pythagorean identity for sine and cosine. So instead of writing sine squared here, I will write 1 minus cosine squared theta, and then multiply that by d theta. Okay? And now we can use u substitution to finally get this integral into a form that we can integrate. If we set u equal to cosine theta, its derivative, which is negative sine, you can find within the integral. Maybe not the negative part, but you can find sine, which is the most important part. Okay, so I'm going to set u equal to cosine theta, and the derivative of u with respect to theta is negative sine theta. And then solving for du, you want to multiply both sides by d theta. So we have du is equal to negative sine theta d theta. But you want to make sure that whatever du is equal to, you can find that in the integral. And I don't see a negative sine theta d theta, I just see a positive sine theta d theta. So multiply both sides by negative 1, and then we'll have a proper substitution for du. We'll have negative du is equal to sine theta d theta. All right, so now let's rewrite this integral in terms of u. This will be equal to 1 divided by the square root of 3 times the integral of 1 minus u squared times negative du, right? We replace cosine theta with u because that's what we set it equal to. So instead of cosine squared, we have u squared. And then we replaced sine theta d theta with negative du because that's what we found that was equal to. Okay, and so then pulling this negative out to the front and integrating 1 minus u squared, we get that this is equal to negative 1 divided by the square root of 3 times the integral of 1, which will just be u, minus the integral of u squared, which if you add 1 to the exponent and divide by that new exponent, you'll get u cubed divided by 3. And then don't forget about the constant of integration plus c. Okay, but then we want to go back into terms of theta, right? We want to substitute back what we set u equal to now that we have integrated, and u is equal to cosine theta. So we want to replace each of those u's with cosine theta. So let's do that here. This will be equal to negative 1 divided by the square root of 3 times cosine theta minus 1/3. I'm just going to pull that 1/3 out front, and that's multiplied by cosine cubed theta plus c. All right, so now we're back into terms of theta, but we're actually not done yet, because remember, our original integral was in terms of x, right? We used a trig substitution to get it in terms of theta, so that we could then eventually integrate it as we did. And so now that we did integrate, we need to go back into terms of x. We need to rewrite cosine theta and cosine cubed theta in terms of x. So let's work on that here. In order to determine what cosine theta is equal to in terms of x, we need to revisit our original substitution. Because from this equation, we can determine the relationship between the angle of theta and this value of x, right? Because if we solve for tangent in this equation, if we divide both sides by the square root of 3, we get the equation that tangent theta is equal to x divided by the square root of 3. And we know that trig functions can be used to relate an angle of a right triangle to the different sides of that right triangle. And so if I draw a right triangle here, let's say that this angle right here is theta. We know that tangent theta is equal to the opposite side divided by the adjacent, right? Just remember SOH, CA, TOA. Sine is the opposite divided by the hypotenuse, cosine is the adjacent divided by the hypotenuse, and tangent is the opposite divided by the adjacent. Okay, so using that here, if tangent theta is equal to x divided by the square root of 3, then the opposite side is x, and the adjacent side is the square root of 3. So we have x and the square root of 3, which then means that the hypotenuse would be the square root of the sum of the other two sides squared. So if you take the square root of 3 and square it and add that to x squared, and then take the square root of that, you get the square root of 3 plus x squared. That would be the length of the hypotenuse using the Pythagorean theorem. Okay, so we have the square root of 3 plus x squared. And now that we have those three sides of the triangle identified, we can rewrite cosine theta in terms of x. Because using this triangle, we know that cosine of theta, or cosine of that angle, will be equal to the adjacent side divided by the hypotenuse, right? Remember from SOHCAHTOA that cosine is the adjacent divided by the hypotenuse. Okay, so the adjacent side is the square root of 3, and the hypotenuse is the square root of 3 plus x squared. So here's what we get rewriting our answer here, but in terms of x, we have -1 divided by the square root of 3 times cosine theta, which is the square root of 3, divided by the square root of 3 plus x squared, minus 1/3 times cosine cubed theta. So just write this expression again, but cube it. So 1/3 is multiplied by the square root of 3 divided by the square root of 3 plus x squared, quantity cubed, and then plus c. Okay, now technically this would be the correct answer. It is the solution to this integral in terms of x, but we can simplify it a little bit to make the answer look nicer. So let's do that yet. First thing I'll do is distribute -1 divided by the square root of 3 through this quantity. So this will be equal to the negative square root of 3 divided by the square root of 3 times the square root of 3 plus x squared. But now those square roots of 3 will cancel out, so we'll take care of that in the next step. But then multiplying -1 divided by the square root of 3 times this term will make it positive, so we'll get plus 1 divided by 3 square roots of 3, multiplied by the square root of 3 cubed, so multiply the square root of 3 by itself 3 times, which will be 3 square roots of 3, divided by this denominator to the power of 3. And so the square root of 3 plus x squared would be 3 plus x squared to the power of 1/2. So if you cube it, multiply 3 by that power of 1/2, and you'll get 3 plus x squared to the power of 3/2. And don't forget, plus c. And then finally, 3 square roots of 3 will cancel out with that 3 square roots of 3, giving us that the integral is equal to -1 divided by the square root of 3 plus x squared plus 1 divided by 3 plus x squared to the 3/2 power plus c. And that right there is the final answer to this problem. That is the integral of this expression. Okay, so it took a lot of steps to get here, but that's par for the course with trig substitution problems. Next up, for problem 13, we want to use cylindrical shells to find the volume of the solid that results from revolving the region enclosed by y equals x times e to the power of x, y equals 0, x equals 0, and x equals 2 around the y-axis. Okay, so this problem is clearly telling us to use the shell method to find the volume of a solid of revolution, right? We are told to use cylindrical shells to find that volume. So there's no question about what method we need to use here. The problem is pretty clear about that. We just need to determine how to set up the integral for the shell method that will actually calculate the volume here. And so as with most shell method problems, I do recommend that you draw a graph of the region that is going to be revolved to form this solid of revolution. And so let's work on that here first. I'll draw my y-axis like this, and then here is my x-axis. The first curve, or the first boundary that we're given here, is y equals x times e to the power of x, which perhaps is not a function that you are very familiar with its graph. And so if you wanted to, you could plug in a couple values of x to get some output values of y to figure out the general shape of that curve. So you could plug in x equals 1, x equals 2, x equals 3, and so on until you think you have enough points to get this shape. But I'm not going to go through all of those steps here. I'm just going to give you a rough sketch of what this curve looks like if you were to do that, or perhaps you just want to use a graphing calculator. Either way, that curve will look something like this. Okay, don't worry about the detail over here that I added. Really, all we're worried about is this part of the curve right here. That is y equals x times e to the power of x. All right, and then y equals 0 is the x-axis, so I'm not going to bother to graph anything for that. Just remember that that is one of the boundaries. X equals 0 is the y-axis, so in the same way, we don't really need to graph that. Just remember that it is a boundary, and then we also have x equals 2. And I will graph that, so let's say that this right here is x equals 2, and then I'll draw a line like this. Okay, so that will represent x equals 2. Now, as you're going to quickly realize, this is not drawn to scale at all. This is a sketch of the region, which would be this little region right here. But what I mean by it not being drawn to scale is because if you were to look at the y value for where x equals 2 intersects with this curve, you would just want to plug 2 in for x in this equation, and you would get y is equal to 2 times e squared, which is approximately equal to 14.77. So this y value right here would be 14.77, but it looks like it's y equals 3 the way that I've drawn it. Okay, so this is not a perfect sketch. I'm just going to say that this right here is about 14.77, and that's going to be good enough because really all we want to make sure that we can identify are the curves and lines that bound our region. As long as those are in the right places, as they are here, that's good enough to help us set up an integral to calculate the volume. Okay, and so let's actually work on that now. Remember that we are going to revolve this region around the y-axis, so I'll make a note of that here. And that's important to identify because when you're using the shell method and you're revolving around the y-axis, you want to work in terms of x. Okay, so let's set up the integral for calculating the volume using the shell method. Remember that the volume will be equal to 2 pi times the integral from a to b, which are the values of x that the region lies between, and that will be of r of x, the radius function, which represents the radius of the cylindrical shells, and that's multiplied by h of x, the height function, which represents the height of the cylindrical shells. And so we multiply that by dx, and that is the formula that we need to set up. Now, when we're revolving around the y-axis, not some other vertical line, the radius function, when working in terms of x, will just be x. Okay, so we will have 2 pi times the integral from a to b, and I'll get to those bounds in just a second, but r of x is equal to x. Okay, and so then that will be multiplied by the height function. Now for the bounds of integration, what are the two values of x that our region lies between? Well, it's between x equals 0 and x equals 2. So we integrate from 0 to 2, and then for the height function, what will be the height of the cylindrical shells? Well, what you want to do is look at the region from the top down and take the top function of the region minus the bottom function. So in this case, the top function is x times e to the power of x, and the bottom function is the x-axis, or y equals 0. So the height function is x times e to the power of x minus 0, and then we have dx. Okay, so now we have set up the integral. Now all we have to do is simplify it and solve it. And so x times e to the power of x minus 0 is just itself, but then it's being multiplied by x, so we'll have x squared times e to the power of x. All right, so this is equal to 2 pi times the integral from 0 to 2 of x squared times e to the power of x dx. And so now, how do we integrate this expression? Well, what we have here is a product of two different types of functions. We have an algebraic function of x squared and an exponential function, e to the power of x. This is a prime example of where we want to use integration by parts. And if you've had a lot of practice with using integration by parts, you might recognize this to be an integral where we will have to use it twice. Okay, so you'll see that in just a little bit, but let's just work on using integration by parts the first time. We have to pick something within the integral to set equal to u, and then set everything else equal to dv, right? Because remember the formula for integration by parts is that the integral of u dv is equal to u times v minus the integral of v du. Okay, so currently our integral is in this form. We need to rewrite it in this form. And the way I typically recommend that you choose your u is whatever is going to get simpler when you take its derivative. Most of the time that will lead you in the right direction. And in this case, x squared gets simpler when you integrate it. It goes from being a quadratic expression with a power of 2 to just a linear expression with a power of 1. All right, e to the power of x, on the other hand, when you take the derivative of it, just stays the same. So let's do that. We'll let u be equal to x squared, which means that dv will be equal to everything else, that being e to the power of x times dx. Okay, so we have e to the power of x dx, and now we want to take the derivative of u with respect to x, so you'll get du dx equals 2x, right? 2x is the derivative of x squared. And then you want to solve for du by multiplying both sides by dx. Okay, so I'm just going to rewrite that here. We'll have du is equal to 2x dx. And then we want to integrate dv, and the integral of e to the power of x dx will just be e to the power of x. The integral of that function is just itself, so we get v is equal to e to the power of x. Okay, and so now we can rewrite this integral using the formula for integration by parts. This will be equal to 2 pi times this integral, but now we are going to rewrite it in this way. So I'm going to have u times v, which is x squared times e to the power of x, minus the integral of v du. So you'll have e to the power of x times 2x dx. I'll write that like this. We have 2x times e to the power of x dx, and then that will be evaluated from 0 to 2 when we're done integrating. Okay, so we've used integration by parts one time, but we will have to use it again, because if you look at this integral here, we have another product of two different types of functions. We now have x to the first power times e to the power of x. So it did get simpler. This integral is easier than what we started with, but we still need to use integration by parts one more time before we will have an integral that we can actually integrate. Okay, so let's work on that here. If you want, you could use different letters for u and v for the second set of integration by parts values, or you could use a subscript of u1 and v1, and then use u2 and v2. Whatever you have to do to stay organized, feel free to do that. What I'm going to do, though, is just use a different color. So for this integral, we can leave the 2 on the outside. In fact, I'm just going to rewrite that here. We'll have minus 2 times the integral of x e to the power of x. I will choose to let x be u again, because it's going to get simpler when I take its derivative. So I'll let u be equal to x, and then dv will be equal to everything else, which will be e to the power of x times dx again. All right, we have e to the power of x dx. This part right here is what I set equal to dv, and this part right here is what I set equal to u. But then taking the derivative of u, you'll just have the derivative of x, which is 1, so du divided by dx is equal to 1, and multiplying both sides by dx gives you that du is equal to dx. Then for dv, if you integrate that to get back to v, the integral of e to the power of x is once again e to the power of x. So you get v is equal to e to the power of x. So then rewriting this integral, this will be equal to 2 pi times x squared times e to the power of x minus 2 times this integral, which we are now rewriting with this formula. U times v will be x times e to the power of x. So I'll write x times e to the power of x minus the integral of v du. So we'll have e to the power of x times dx. Okay, so e to the power of x times dx. Close that parenthesis, and all of that is evaluated from 0 to 2, and then all of that is multiplied by 2 pi. And so now we're done with integration by parts, because the integral that we're left with here is now something that we can actually integrate. In fact, we've already done this integral specifically 2 times already. We already took the integral of e to the power of x dx when setting up our integration by parts. We know that this is just going to be equal to e to the power of x. Okay, so now let's do that and then evaluate our integral at these bounds of integration to get our final value for the volume of the solid of revolution formed by revolving this region around the y-axis. And so integrating this integral and then simplifying a little bit, this will be equal to 2 pi times x squared times e to the power of x, and then this negative 2, I'm going to distribute it through this quantity, so you'll have negative 2 times x times e to the power of x, so I'll write that minus 2 times x e to the power of x, and then multiplying negative 2 by the integral here, those negatives will cancel out, so you'll have positive 2 times the integral of e to the power of x, which is just itself. So we have plus 2 e to the power of x, and that's all evaluated from 0 to 2. All right, so now we want to plug 2 into this expression, and then subtract plugging in 0. Doing that, we will get 2 pi times plugging 2 in for x, so we have 2 squared times e squared minus 2 times 2 times e squared plus 2 times e squared. Then we will subtract plugging in 0, so 0 squared times e to the power of 0 minus 2 times 0 times e to the power of 0 plus 2 times e to the power of 0. All right, now both of these terms go to 0 because within them we are multiplying by 0. So they are just equal to 0. But then going back over here, let's simplify. We have 2 pi times 4e squared minus 4e squared plus 2e squared minus 2 times e to the power of 0. And e to the power of 0 is 1, so you have 1 times 2, which is 2. So we are subtracting 2. All right, and then we have a positive 4 times e squared and a negative 4e squared. So those will cancel each other out. They combine to be 0, leaving us with 2 pi times 2e squared minus 2. And so that would be our final exact answer. We can make it look a little bit nicer if you pull out a common factor of 2 from these two terms. Bringing that out to the front and multiplying it by 2 pi, we get 4 pi times e squared minus 1. And that right there would be the volume of the solid of revolution formed by revolving this region around the y-axis using cylindrical shells. In particular, that is the exact answer, which is generally how I recommend you give your answers, but if you did put it into a calculator, it's approximately equal to 80.287 and some more decimals. Okay, so that's about what the value is, but I always like to box in the exact answer as my final answer. Okay, but with that, that is it for this problem. Let's move on to the next one. Next up, for problem 14, we want to find the radius and interval of convergence for the power series. And our power series is the sum from n equals 1 to infinity of negative 1 to the power of n times x minus 1 to the power of n divided by n times 3 to the power of n. Okay, so remember, to find the radius and interval of convergence for a power series, you want to use either the ratio test or the root test on that series. I typically always use the ratio test, but if you want to use the root test, that's fine, that will work too. But if I use the ratio test here, remember that we need to set up the limit as n approaches infinity of the absolute value of the a sub n plus 1 term for the series divided by the a sub n term. All right, so in this case, a sub n is just equal to the expression in the series. It is negative 1 to the power of n times x minus 1 to the power of n divided by n times 3 to the power of n. But then for a sub n plus 1, what we'll have is this same expression, but where all of the n's become n plus 1. So we have negative 1 to the power of n plus 1, then x minus 1 to the power of n plus 1, and then that is going to be divided by the quantity n plus 1 multiplied by 3 to the power of n plus 1. Okay, remember to put parentheses around that quantity of n plus 1, because just like n is being multiplied by 3 to the power of n, the entire quantity of n plus 1 must be multiplied by 3 to the power of n plus 1. And so then setting up the limit for the ratio test, we're going to have a sub n plus 1 divided by a sub n, and instead of writing out that complex fraction of one fraction divided by another, what I like to do is write a sub n plus 1 and then multiply it by the reciprocal of a sub n, which is the same as dividing by that term. Okay, so here's what that will look like. We'll have the limit as n approaches infinity of the absolute value of a sub n plus 1, so negative 1 to the power of n plus 1 times x minus 1 to the power of n plus 1, and then that is divided by n plus 1 times 3 to the power of n plus 1. And then that would be divided by a sub n, but like I said, instead of dividing by that fraction, I'm going to multiply by its reciprocal, and that will accomplish the same thing. So just flip the numerator and denominator, and then multiply. So we have n times 3 to the power of n divided by negative 1 to the power of n times x minus 1 to the power of n. Okay, so this is the limit that we have to work with here. Now what we want to do is evaluate it, but first there are some simplifications that we can make, or some things that we can cancel out. For one thing, we are going to be taking the absolute value of this expression. So this negative 1 to the power of n plus 1 and this negative 1 to the power of n, we can get rid of those because all those pieces do is alternate the sign of their corresponding expressions, right? It just changes the terms from being positive or negative. So if we're taking the absolute value of this expression, it will never be negative, meaning that these two pieces will always be equal to 1, which don't matter because anything multiplied by 1 will be itself. Okay, so that takes care of those two pieces. But then something else that we can do is split up these powers. We can have x minus 1 to the power of n multiplied by x minus 1 to the power of 1. Same thing down here. We can split this power up and have 3 to the power of n times 3 to the first power. Okay, so let's do that down here. Our next step is to have the limit as n approaches infinity of the absolute value of x minus 1 to the power of n times x minus 1 times n times 3 to the power of n divided by n plus 1 times 3 to the power of n times 3 to the first power times x minus 1 to the power of n. Okay, so I just multiplied everything together here into one fraction, and I also split up those powers that I mentioned before. And by doing that, we can now see that there are some more pieces that we can cancel out. We have a 3 to the power of n in the numerator and denominator, so they cancel out. Anything divided by itself is 1. And we have x minus 1 to the power of n in the numerator and denominator as well. So those cancel out too, just leaving us with x minus 1 times n in the numerator and n plus 1 times 3 in the denominator. Okay, and so at this point, the absolute value bars, we do still need them, but not around the entire expression, because the values of n that we're working with are always going to be positive, right? For the series, n goes from 1 to infinity, so we're not worried about negative values of n. The only part of this expression that could be negative is anything involving the variable of x. Okay, so I'll keep the absolute value bars around x minus 1, but then separate it from everything else. And so here's what I mean by that. This will be equal to the limit as n approaches infinity of n divided by 3 times n plus 1 times the absolute value of x minus 1. Okay, so we still have that n from the numerator, and then 3 times n plus 1 in the denominator, but then I separated that expression involving n from that quantity of x minus 1, which now has the absolute value bars around it. And now we can go ahead and evaluate this limit, right? Remember that this is a limit as n approaches infinity, and so with respect to n, the absolute value of x minus 1 is just a constant. We're not looking at a limit for x here, we're looking at a limit for n. So just focus on this piece of the limit, and whatever the value of that limit is will be multiplied by the absolute value of x minus 1. Okay, and so how do we evaluate this limit here? Well, remember, when you have a limit at infinity of a rational expression with just algebraic or polynomial expressions in the numerator and denominator, a quick trick for evaluating the limit is if the highest power of n in the numerator and denominator is the same, then that limit at infinity will be equal to the ratio of their coefficients. Okay, so in this case, notice that the numerator and denominator have the same highest power of n, that being n to the first power, so the limit will be equal to the ratio of their coefficients, meaning it will be 1, the coefficient of this n, divided by 3. That would be the coefficient of this n. If you multiply this 3 through this quantity, you'd have 3n plus 3. The coefficient of n is 3. So the limit is equal to 1/3, right? 1 divided by 3, and that is multiplied by the absolute value of x minus 1. Just a quick side note, if our powers of n were not equal, if the denominator had a bigger power of n, then that limit at infinity would be equal to 0, and if the higher power was in the numerator, then that limit would be equal to infinity. Okay, so those are just some quick shortcuts that you want to remember for these limits at infinity when you're doing the ratio test. But putting that aside, we now have 1/3 multiplied by the absolute value of x minus 1 as a result of the ratio test. And so where do we go from here? Well, remember, we're trying to determine for what values of x does this power series converge. And so if we're thinking about the ratio test and how it works on a regular series that's not a power series, we know that the series converges if this limit for the ratio test is less than 1. So we're going to use that here. We're going to set our result less than 1 and then solve for x. That will give us the interval of convergence, or the values of x for which this expression is less than 1, which means that this power series converges for those values of x. Okay, so let's work on that. The first thing that we would want to do here is get rid of that 1/3, so multiply both sides by 3, and here's what you'll find. You'll get the absolute value of x minus 1 is less than 3, right? Multiplying both sides by 3 gets rid of that 1/3, but then this 1 becomes 3, And then at this point right here, we can actually determine the radius of convergence for the power series. Whenever you get this statement from the ratio test or the root test, where you have the absolute value of just the expression involving x less than some value, then that value is the radius for the power series. Okay, so we just found here that r is equal to 3. That's our first answer to this problem, but we still need to find the interval of convergence. So let's keep going here. We can rewrite this inequality like this, get rid of those absolute value bars, and just say that -3 is less than x minus 1, which is less than +3. Okay, that is how you can rewrite this inequality involving the absolute value bars. These two statements mean the same thing. Then what we want to do is solve for x, so get rid of -1 by adding 1 to each part of this inequality. So what we get is -2 is less than x, which is less than 4. And that right there is our interval of convergence, at least without checking the endpoints. We're not quite done yet, but so far we do know that the interval of convergence will at least include all the values of x between -2 and +4. We're just not sure if -2 and +4 are included themselves. We still have to check that before we finish this problem. And all that entails is plugging -2 in for x in the power series, and then testing to see if that series is convergent or divergent, and then doing the same thing for 4. We'll plug 4 in for x in the power series, and see if the resulting series is convergent or divergent. So we may need to use some other series tests here to figure that out. So let's work on that next. Let's start by checking the endpoint for x equals -2. So if we look at x equals -2, plugging that into the power series, we'll have the sum from n equals 1 to infinity of -1 to the power of n times x minus 1, so -2 minus 1 to the power of n, divided by n times 3 to the power of n. Okay, so now we want to simplify. -2 minus 1 is -3, so I'm just going to rewrite that right here. We have -3 to the power of n. But before we try to determine if this series converges or diverges, we should try to simplify it as much as possible, because that might help us avoid any potential extra work. And what I notice here is that we have -3 to the power of n. We could rewrite that as well. We could break it up into -1 to the power of n times 3 to the power of n, right? This would be equal to the sum from n equals 1 to infinity of -1 to the power of n times another -1 to the power of n times 3 to the power of n. Now, just to make sure it's clear why that is the case, it's just like if you had x squared times y squared. They're both to the power of 2, so you could rewrite it as x times y squared. It's just that in this case, what we have is -3 to the power of n, so you can break that up into two pieces of -1 to the power of n and 3 to the power of n. You can keep that same exponent, but then just multiply the bases. -1 times 3 is -3. So we're just reversing that process to get these two pieces. And the reason why that's helpful is because now we have a 3 to the power of n in the numerator and denominator that will cancel out. So those are gone, which makes the series much simpler. And then in the numerator, we have two of those expressions of -1 to the power of n, which will cancel each other out, right? Whenever this one is +1, this one will also be +1. So you just have 1 times 1, which is 1. Or the other option is that they'll both be -1 at the same time, and -1 times -1 is also +1. So no matter what the value of n is, the numerator will always just be 1. So we can rewrite this series again and have the sum from n equals 1 to infinity of 1 divided by n. And that is a much easier series to work with, because what that is the harmonic series. That is a p series where the value of p is 1. We know that this is a divergent series by definition. Okay, so that's our conclusion for x equals -2. The resulting series for the power series is the harmonic series, which is a divergent series. And so because that series diverges, we can conclude that -2 is not included in the interval of convergence. So leave this parenthesis open. We will not change it to a closed bracket. -2 will remain excluded from that interval. But what about +4? We still need to check that value of x yet. So let's do that. Let's let x be equal to +4. Doing that, we'll get the sum from n equals 1 to infinity of -1 to the power of n times x minus 1, so 4 minus 1 to the power of n, divided by n times 3 to the power of n. Now 4 minus 1 is 3, so this is just 3 to the power of n. I'll even rewrite that here. This would be 3 to the power of n. And so we have 3 to the power of n in the numerator and denominator, so those can be canceled out, and what we get for the series here is a sum from n equals 1 to infinity of negative 1 to the power of n divided by n. This series is very similar to our harmonic series from before, but this one is an alternating series. We still have that negative 1 to the power of n in the numerator, and it doesn't cancel out with anything, it has to stay there. So in order to determine if this series converges or diverges, we need to use a different test. We can't say that this series diverges automatically like we could with this one. And so I'll choose to use the alternating series test here. Remember that for the alternating series test, there are two different conditions that you want to check. Firstly, you want to check that the limit as n approaches infinity of a sub n from the series, not including the alternating part, you want to check that that limit is equal to 0. So let's set that up. We'll have the limit as n approaches infinity of just 1 divided by n, right? You set up the limit as n approaches infinity of the general term from your series, but without the alternating part. So that is just 1 divided by n. And we know that that limit is equal to 0 because you would have 1 divided by infinity if n is approaching infinity, and a fixed value divided by infinity will approach 0 for a limit. So that checks out. The first condition is met. And then the second condition is that that expression that we just took the limit of is decreasing. And so there's a couple different ways to go about this. You could set it up as a function. You could let f of x be equal to 1 divided by x, take its derivative, and if that derivative is negative, you could conclude that it is decreasing. But since this is a relatively simple expression, we can just do a direct comparison between terms. We just need to show that the next term is smaller than the previous term, or perhaps equal to, but generally you want to be trying to show that it's smaller. Okay, so if we set that up here, the a sub n term is 1 divided by n, and that needs to be greater than or equal to the n plus 1 term, which is just 1 divided by n plus 1, right? You just replace n with n plus 1, and there it is. And this is very clearly a true statement, because if the numerators are the same for these two expressions, then what's going to determine their value is the denominator. And as you increase the value of the denominator of a fraction, the overall value of the fraction gets smaller. Right? The bigger the denominator, the smaller the value. So this expression of 1 divided by n plus 1 will be less than or equal to 1 divided by n. So that checks out. This is in fact a decreasing expression, that being 1 divided by n, which means that the second condition for the alternating series test is also met. So since both of the conditions are met, we can conclude that this series is a convergent series, which means that the power series converges when x is equal to 4. So it should be included in the interval of convergence. So let's change that here. The open parenthesis is gone, and we will replace it with a closed bracket. And that would complete this problem. We now have both the radius and interval of convergence for the power series that we were given here. That is it for this problem. Okay, let's take a look at the last review problem for this video. Alright, so this is the last review problem for this video here on YouTube. I do have more, but I'll talk about that after we finish this problem. So stay tuned if you want to know how to get all of the other review problems. But let's work through this problem first. For problem 15, we want to find the arc length of the curve y equals x squared minus 1/8 times the natural log of x over the interval from 1 to 2, including both of those endpoints. Okay, so these instructions are pretty straightforward. We know we want to find the arc length of a curve. We've been given that curve, and we have the interval for which we want to find the arc length over. So what we need to do here is set up the integral to calculate the arc length. Remember that the formula looks like this. The arc length L is equal to the integral from a to b, which represent the endpoints of the interval for which we want to calculate the arc length. But then inside the integral, we have the square root of 1 plus the derivative f prime of x squared times dx. Okay, so in order to set up this integral, we will need the derivative of our curve. And since it's given to us as y equals x squared minus 1/8 times the natural log of x, I'll just rewrite this f prime of x as y prime. All right, that way our notation matches up. And so let's find that derivative. Let's take the derivative y prime of our curve given by y. We are going to take that derivative with respect to x. And so starting with the first term here, the derivative of x squared is 2x. So we have 2x minus 1/8 times the derivative of the natural log of x, which is 1 divided by x. Okay, and so you can multiply those denominators and have 1 divided by 8x. In fact, that's how I will rewrite it right here. The derivative is 2x minus 1 divided by 8x. Okay, and so now we have everything we need to set up this integral to calculate the arc length. So let's do it. This will be equal to the integral from a to b, which comes from the interval that we're given. So the lower bound will be 1 and the upper bound will be 2. And then we have the square root of 1 plus y prime squared, or the derivative squared. So let's put in that derivative, 2x minus 1 divided by 8x squared, and then dx. Okay, and so now our arc length integral is fully set up. All we need to do now is solve it. And in its current state, we can't really integrate this expression. So let's try to simplify it or modify it in some way so that we can integrate it. I think a good place to start is to square this quantity. So let's do that here. We're still going to have the integral from 1 to 2, and then the square root of 1 plus, but then let's square this quantity. I'm going to do it the quick way. I'll start by squaring the first term. So you'll have 2x squared, which will be 4x squared. And then the next term will be these two terms multiplied together, but then multiplied by 2. I'll write that out. We're going to have plus 2 times 2x times negative 1 divided by 8x. And then for the last term, we will have this term squared. And so the numerator will still be 1 because 1 squared is 1. But then squaring 8x, you get 64x squared. All right, and that is still underneath the square root. And then we have dx on the end. Now simplifying a little bit, we have 2 times 2, which is 4. So 4x divided by 8x, those x's will cancel out, and then 4 divided by 8 is 1/2. So this simplifies to the square root of 1 plus 4x squared minus 1/2 plus 1 divided by 64x squared. Okay, and so then that is multiplied by dx. Again, just to be clear, these two x's canceled out, so just cross those out. And then 2 times 2 is 4, divided by 8 gives you 1/2. So this whole term is just negative 1/2. All right, and then we can combine like terms here. We have negative 1/2 and positive 1. 1 plus negative 1/2 is positive 1/2. So if we combine them, we will get the integral from 1 to 2 of the square root of 4x squared plus 1/2 plus 1 divided by 64x squared dx. All right, but now where do we go from here? Because this is still an expression that we really don't know how to integrate. There's no specific integration techniques or rules that we have learned for an expression like this. So what do we do here? Well, a common strategy for more complicated integrals in these arc length problems is to try to eliminate the square root in some way. Usually that would be because of what's underneath it. Sometimes you'll be able to manipulate the expression underneath the square root such that it is a quantity squared, such that the square root would cancel out with that squared quantity. But it doesn't really look like we have that at first. However, this expression underneath the square root can be factored. We can factor this into being a quantity squared. In fact, we can make use of some of our previous work to help us figure out what those factors would be. And what I mean by that is that these three terms right here, 4x squared minus 1/2 plus 1 divided by 64x squared, these three terms were the result of expanding this quantity squared, and the only difference between these three terms and the three terms we have now is this was negative 1/2 and this is positive 1/2. In other words, we can factor this expression using this same quantity squared, but just make that minus sign a plus sign. Because squaring 2x still gets you 4x squared, squaring the last term still gives you 1 divided by 64x squared, and then that middle term is these two terms multiplied together, multiplied by 2, but if this is a plus sign, then instead of being negative 1/2, it will be positive 1/2. Okay, so what we can do here is this. We can rewrite the integral as the integral from 1 to 2 of the square root of 2x plus 1 divided by 8x squared, and then dx. All right, and then that square root and this quantity being squared will cancel out, just leaving you with 2x plus 1 divided by 8x, which is something that we can integrate. And we'll do that in a second, but just a side note here, if you were not able to recognize that this is a very similar expression to what we had earlier, and so you could take advantage of that to quickly factor this expression, Another strategy that you can use that would get you to this same result is just try to come up with some factor that when squared results in those terms underneath the square root. Okay, if you notice that you have a quadratic expression, take the square root of the first term and the last term, and then put them into a quantity squared and see if that would expand to be those terms. If it's off by a negative sign, then perhaps you want to change that sign, but that is something that you can try to do if you have a square root of a quadratic expression and you're not sure how to integrate it. It's very likely that you'll be able to factor it into a quantity being squared that will then cancel out with the square root. Okay, so always be on the lookout for that. But now back to our integral. As I pointed out, this square root will cancel out with this quantity being squared. So now we have the integral from 1 to 2 of just 2x plus 1 divided by 8x dx. Okay, and so now let's integrate each term. To integrate 2x, you want to add 1 to the exponent and then divide by that new exponent. So this will become x squared, and then dividing by 2, that will cancel out with this 2. So you will just get x squared, but I will write it out. We'll have 2 times x squared divided by 2, and then that will be added to the integral of 1 divided by 8x. And the integral of 1 divided by x is a natural log of the absolute value of x. So you'll get 1/8 multiplied by the natural log of the absolute value of x. And then that will be evaluated from 1 to 2. Okay, so then as I pointed out, these 2's will cancel out, but then you want to evaluate this expression at 2 and subtract the evaluation at 1. So plugging in 2, we get 2 squared plus 1/8 times the natural log of 2. No need for the absolute value bars because 2 is positive. Same thing with 1. If we plug that in, we will be subtracting 1 squared plus 1/8 times the natural log of 1. And this is interesting because the natural log of 1 is equal to 0. Okay, so this whole term here becomes 0, meaning you just have 1 squared, or just 1, being subtracted from this expression. And 2 squared is 4, so we have 4 plus 1/8 times the natural log of 2 minus 1, and that negative 1 and that 4 combine to be positive 3. So I'll just change that right here. And that will be our final answer, at least in its exact form. 3 plus 1/8 times the natural log of 2 is the arc length of this curve over the interval from 1 to 2. And if you put this into a calculator, you will find that it's approximately equal to 3.0866 and some more decimals. Okay, so that gives you an idea of the size of that arc length, but generally you want to give the exact answer as your final answer. And so with that, this was the last review problem for this video here on YouTube. However, I do have 15 more review problems, just like these, but obviously different problems, that will test your knowledge on Calculus 2 topics. I have those available exclusively on my membership site, JK Math Plus. So if you want to get some more practice before your Calc 2 final exam, feel free to look into becoming a member. You can find all the details about the membership site as well as how to join by heading on over to my website at jkmathematics.com/plus. There's a whole lot more on there than just 15 more final exam review problems. You get access to my private community where you can post problems and ask me questions, and you also get access to my other Calculus 2 bonus videos as well. Not to mention that there's also bonus videos for other math courses that I have covered on the channel as well, such as Calculus 1 and Calculus 3, or any other courses that I cover in the future. And also any comments you leave on those videos are guaranteed to get a response from me. So I know it will provide you with a lot of value. Alright, but with that, that is it for this video. If you have any questions about any of the review problems that we worked through in this video, please feel free to leave those in the comments. But if you don't have any questions, then that is all I had for now, so I will see you next time.